Dr. Harlich from Max Planck Institute and George August University, Göttingen, from Germany. The title is Complexity and Chaotic Dynamics of Cardiac Arrhythmias.
Yeah. Thank you. Yeah, thank you very much for the introduction and for inviting me to this very nice place and this interesting conference. It's really a pleasure to be here. Yeah, the talk is entitled Complexity and Chaotic Dynamics in Cardiac Dynamics, in particular in arrhythmias. So if you go to your medical doctor because you may have a problem with your heart, he or she may do a measurement of your electrocardiogram. And this is a signal which you know probably, maybe you have seen this treatment or have had it in your own case. And you see here heartbeats. These are the QRS complexes. This is a normal heartbeat. Everything is more or less fine. But in this case, you see suddenly a transition to a signal which has a higher frequency. It looks more like a sinusoidal oscillation. And then you see another transition here to a signal which is even more complex. And this is an indication of so-called fibrillation. And the question is, what's going on there? So to understand this, you have to look at the electrical excitation waves in the heart muscle, which causes the contraction of the heart. So in the case of the normal heartbeat, the sinus atrial node initiates a plane wave. A physicist would call this just a plane wave, which is starting at the apex of the heart, and then it's moving in this direction and it leads to the contraction. I will go into more details in a moment. But you can also have a situation, and this is underlying this state of tachycardia, where you have rotating spiral waves in the heart because the heart muscle is an excitable medium. And this rotation frequency of these waves is exactly the frequency that you see here then in the ECG signal. Now, in this case, it's a more or less periodic motion. Okay, fine, it's a stable spiral wave. But things may become worse because this spiral wave may become unstable. And then it turns into a spatial temporal chaotic state, as you can see here. And this is the dynamics underlying the fibrillation signal. And you can imagine, if you have this state, the heart is not contracting coherently anymore. There is no pumping functionality. There is no oxygen supply to your brain and other organs. In other words, after 2 minutes or so, you are dead. That's why this state has to be stopped immediately, and this is the task of defibrillation. We will talk about this. Now, a few words about the heart. Of course, you know the heart is an important organ in our body. It's pumping the blood. It consists of cardiac muscle fibers, as you can see here in this enlargement. And along these fibers are cardiac muscle cells. They are connected by so-called gap junctions, and this is the electrical coupling between them, which is important for the propagation of electrical excitation waves. And here you see a single ventricle cell, so a cell from the ventricles, not from the atria, and you see how it is contracting along its axis. And so this is the cell which is contracting, and as I told you already, there is excitability, because we can generate an action potential very similar to neurons. Actually, heart muscle cells and neurons have a lot in common. And this means if you look at the cell membrane voltage, so this is just a sketch of a cell, we measure the voltage across the cell membrane, and this is time, and then you are first in a resting state, there is an equilibrium, and then you can stimulate this cell electrically by adding a current, for example. If the stimulation is small, the voltage goes back to its equilibrium value very quickly. If the stimulation is above a threshold, then you see this action potential until this voltage goes back to the resting potential. So in this case, there's a cascade of opening and closing ion channels across the cell membrane. I have here only two of them. The sodium channel and sodium ions go in first. Then there is another channel, the potassium channel here, for example. The potassium ions go out. And there are actually many, many more. And different channels for a specific ion types. I will not go into details, but this is basically the mechanism, opening and closing of these ion channels, which is underlying this action potential. Now, the action potential looks a bit different if you look at ventricular cells or atrial cells or the sinus node, but in principle, the mechanism is always the same. Important point is that after such an excitation, you have to wait a bit before you can initiate another excitation, and this is the so-called refractory phase, which is typical for excitable systems. Now, if we have such an action potential, this is the blue curve here, then this leads to a calcium release inside the cell, and the calcium release is important for the cell contraction. I will not go into the details of the biophysics here, but just to give the picture that you have to think about. So the electrical excitation induces a mechanical contraction. Okay, that's fine. But the opposite may also happen. Mechanical contraction may lead to electrical excitation because there are so-called stretch-activated ion channels. They open and close due to mechanical stress, and then there's also ions going in or out the cell membrane, and this is then the other direction of coupling. This is called electromechanical coupling. And yeah. Okay, so just to come back, the cardiomyocytes or the heart cells are excitable systems. We have seen this. In general, probably you know this. I just want to summarize this. The features of excitable systems are basically the following ones. You are in a state space of an excitable system. You have a fixed point, which is stable. Then you perturb the system a little bit. If the perturbation is small, the fixed point is stable. The trajectory goes back to the fixed point immediately. But if your perturbation is strong enough, then you have this excursion in state space, and only later the trajectory will go back to the resting state. And this is what is underlying the action potential that we saw in the voltage signal. Now, this works only if the trajectory is back to the fixed point. In other words, there is this refractory time that you have to wait until you can induce another excitation. And if you now couple elements, excitable elements like the cardiomyocytes, then you have an excitable medium in space. So it's a spatially extended dynamical system, which is excitable, which can support the propagation of excitation waves. But again, if there has been excitation at some spot, then there cannot be another excitation at the same location. You have to wait. So there are regions now which are not excitable for a certain period of time. And these are refractory regions or zones. In the existence of these refractory regions means that, as I said already, the waves cannot propagate there, and they can only go to excitable regions. So this is a little cartoon. This is an excitation wave in red. It goes to the right, but there is a refractory zone because there was maybe an excitation immediately before we took this snapshot. This means that the wave can only go here in this direction. It is stopped here, and then afterwards it will spread again behind the obstacle, the refractory region. And this means, if you think about it, it's not difficult to understand. Due to this mechanism, spiral waves are very prominent in excitable media, in any excitable media, independent of the physics, just due to this fact that there is a refractory region and the wave cannot propagate in any direction. Yeah, that's why we see spiral waves almost everywhere. In excitable media, of course. The Belousov-Zhabotinsky was already mentioned yesterday. It's a famous chemical reaction which can lead to the spiral wave formation. But there are also other diseases, like, for example, this inflammatory disease of the tongue, where you can also have spiral wave patterns due to this very general mechanism of excitability. Now, how can we describe this? The motion of the spiral tip is, of course, most interesting, and the spiral tip is associated with the so-called phase singularity. So if you have a spatial temporal system, let's say with two variables, can be more, but we look only at two of them, you can take snapshots of the spiral, but you can also go to one location here and measure the signal in time that you would see here and here. And then you plot the signal in time at this location of this variable and the same of the second variable, and you get here such a periodic orbit because it's a periodic spiral in this simple case here. Then you can introduce an angle here to parameterize the periodic motion, and then you can plot the angle as a function of space, and you see again the spiral wave. But you also see there is one point here where all the colors come together, and this is the point of the phase singularity, which is most interesting because it's co-located with the tip of the spiral. And now you can study the dynamics of these phase singularities. This is a video I took from an interesting webpage by Flavio Fenton and Elizabeth Cherry, the virtual heart. And you can see here in 2D the motion, the excitation motion, and the black dots are the phase singularities. If you look closely, if some of them come very close together, they may annihilate each other, but there can also be a pairwise formation of spiral waves in rotating in opposite directions. In 3D, these are not points, these are one-dimensional objects, filaments of phase singularities, which are shown here, and they describe the motion of these complicated three-dimensional scroll waves. And of course, you can imagine these filaments can have all kinds of features. I will not go into these details here, but just to give you an idea how one could study this, in particular in simulation, but also experimentally. I will come back to this in a moment. Okay, just a few words about the mathematical description of this dynamics. The simplest approach, and this is what we do here, is to use a continuum model, a partial differential equation, reaction diffusion type equation, describing the electrical dynamics. And then the main question is, what is the local dynamics? There are detailed ionic models which describe the dynamics of all the ions going in and out the cell membrane. They have 15, 27, or 44 variables because there are so many ion channels involved, and of course a large number of parameters. So the typical structure is you have one differential equation for the cell membrane voltage, the voltage across the cell membrane, which consists of the diffusion term and all the ions going in and out. And the dynamics of all these ion currents is controlled by so-called gating variables. So H is a vector here. In other words, this is this long set of ordinary differential equations. And this is this ion current here is actually the sum of different ion currents and a potential additional current which is injected to control the dynamics. Okay, so then there are more simple models, and we also use them very often because we are interested in more generic phenomena. For example, the Fenton-Kammer model, which has only 3 variables, or the Bieler-Reuter model with 8 variables. And then there are even simpler models, including the famous Fitzhugh-Nagumo model, but also the Barkley model or the Alyov-Panfilov model. They consist only of 2 variables. One stands for the membrane voltage, and the other controls the currents in some sense. If you are interested to learn more about this, I can recommend this nice webpage in Scholarpedia, where Fenton and Cherry discuss 45 models in detail and compare them. So it's really a zoology of models, but these are the simplest models. We did not take into account here, for example, mechanical motion or fluid dynamics and so on and so on. So, and then in general, you have to do it in 3D, and you have to take into account these fiber directions. So you can make it as complicated as you want using then finite element models. But this is not what I will show here because we are mainly working with simple models to get some qualitative understanding. A few words about what can we measure. We can use, for example, so-called optical mapping. This is a way to visualize the membrane voltage or the calcium concentration of the heart on the surface of the heart. In other words, you can apply it only with extracted hearts in experiments. And the idea is you use a fluorescent dye and you excite the dye, so you shine light on the heart, and then the re-emitted light from the heart, the optical spectrum is shifted independent on the voltage. In other words, you see optically the voltage changes. And to illustrate this, I want to show you an example. This is an extracted heart in the so-called Langendorf perfusion set, which keeps it alive for several hours. So you have time to study it with cameras, you can apply shocks and so on. And here you see an example of a pig heart in the state of ventricular fibrillation. So this is a ventricle, and you see here this complex pattern on the surface of the heart. This is the electrical activity made visible using the fluorescent dyes. And as I told you in the beginning, this has to be stopped immediately because no oxygen supply, and it's really, you will die. And we have a lot of numbers of people who die from this sudden cardiac death phenomenon, not only in Germany, but worldwide. So this is really important. Okay, there are other techniques to measure this. Of course, also ultrasound is possible. There you have here these typical ultrasound images that you also may have seen when you went to your doctor. And then you can, from this, you can extract displacement vectors with a certain tracking procedure. Then you can compute strain rates from these little arrows here describing the displacement. And then from the strain rate as a function of time, you can again get phase information, which is shown here. And then you're in a situation where you can again look for phase singularities, and in this case it's really 3D, so that's why you have then these filaments moving around in the heart, basically. And of course, this is a very complex dynamics, but it is also interesting to study it. And you can combine these techniques in electromechanical imaging. So you have a heart here, you have cameras, you have an ultrasound transducer, and you can, of course, use the cameras to see here the motion from outside. Then you can use optical mapping to see what's going on electrically on the surface of the heart, and use this to get information about electrical rotors or spiral waves on the surface of the heart. And then you can do the same with the ultrasound signal, as I showed in the previous slide. So you get information about mechanical motion, mechanical rotors, and then you can compare them. And in the case of the mechanical rotors, you can again go in 3D to see filaments and their motion in space. And there are different scenarios, how these filaments can form, how can they develop in time. As you can imagine, this is a story of its own. If you are interested, I can recommend this publication where it was shown for the first time that this is possible to see this. And one question is, for example, are the phase singularities of the mechanical motion and of the electrical motion always at the same spot? Are they co-located? Okay, here you see another movie and another example. This is really a human. So this is from bypass surgery in the University Hospital in Göttingen. And you see here the heart in the state of fibrillation. The patient is connected to a heart-lung machine. Therefore, it's not necessary to stop this immediately. You have a few seconds to take videos and measurements. And the measurement is taken here by an ultrasound device, which is inside. And it gives you, for example, this results. If you do the motion tracking in the ultrasound videos and analyze it, and you see this complex pattern moving around, describing the state of fibrillation. Now you can, of course, analyze this. You can compute the mean displacement of these arrows. You can compute the strain rate. In addition, you also have ECG information. And an interesting point is, for example, in this segment of time we are considering here, the ECG looks more or less the same all the time. It's not periodic, yes, because it's a fibrillation state, but we would say, okay, there's nothing happening. But if you look at the displacement signal, there's a clear difference between the signal here in the first part and then later. So this mechanical motion provides even more information or additional information compared to the ECG signal. Now, I said several times we have to terminate this. Okay, so the standard technique to terminate ventricular and also atrial fibrillation is to apply a strong electric shock. And the idea is very simple. If I apply a strong electric shock, then all the cardiomyocytes, all the heart cells are excited at the same time. They will be in an excited state and then in the refractory state, and then later back in the resting state, and then the sinus node can take over again, and normal heartbeat will start again. This is the idea, and in principle it works. You can do this externally with some electrodes here. For people who are known at risk to get this problem, you can implant an ICD device here, which is also generating then a strong electric field from the housing of the device and some electrode which is inside the heart. The problem is you have to do this with a high voltage to make sure that all the cells, or almost all, are excited, otherwise it will not work. In other words, you need high energy, and high energy means high currents, local currents, and this is painful, very, very painful for those patients who are still did not lose consciousness. And it also, of course, may cause damages on the cell level due to the current. And then this is a starting point of the next problem, in a sense. So that's why people would like to avoid this. But before talking about that, let me mention one concept, the so-called dose response curve, to measure the success of the defibrillation as a function of the applied voltage. And these are data from patients, and you can see this typical sigmoid curve. Of course, the higher the voltage, the higher the success rate. No surprise. What we found in numerical simulations, just a side note, is that not only the energy is important for the success, but also the moment when you apply the shock during the episode of fibrillation. You have strong changes in the success rate. You can study this in numerical simulations, but of course it's difficult to apply this immediately to a real situation in the clinics. Okay, now how can we avoid these strong shocks? The idea is to use sequences of weak pulses, not one strong one, but to somehow use the dynamics of the system to stop this state. And these sequences are applied, and an important concept is the so-called virtual electrodes. So what does it mean? In a real heart, so far I showed, in a real heart you typically have heterogeneities. These are blood vessels, scars, fatty tissue, and so on. And if you apply an electric field and you have such a heterogeneity here in the middle, then you get the hyperpolarization and the depolarization in the vicinity of the heterogeneity, conduction heterogeneity. And if this exceeds the threshold for excitation, then you can initiate an excitation wave from the heterogeneity. So it's similar as if you would have stick a metal object into the heart to inject a current, but this is what we do not do. We use the existing heterogeneities to initiate local excitation waves, and this is illustrated here. This is again an electric field which is switched on and off, and you see here the heterogeneity, and then whenever it is switched on, you will see there is a wave emitted from the heterogeneity. Just due to this mechanism, more details about this can be found in these publications. So this is a very important ingredient of the whole thing, because now let's look at this cartoon simulation. This is a heart. The black dots here are heterogeneities of different sizes, and you see here already a snapshot of some excitation waves. Now again, we switch on and off an electric field, and if I start the animation, then you will see whenever we switch on the field, yes, now and now and now, and after a few pulses, the dynamics has changed in a way that it goes to the boundary, and then the state of fibrillation of chaotic dynamics is over. And this has been shown already 15 years ago in experiments that this works in principle. You can see here a heart tissue, and there is again an electric field which will be applied. When I start the movie, you will see it, and you see here the color is again the membrane voltage on the surface using this optical mapping technique with the fluorescent dyes. You see whenever this is red, we apply a pulse, and then if you look carefully, you see larger and larger areas are excited. There is a kind of synchronization effect, and you see after about 5 pulses or so, the hardcore spectral sinus rhythm in these experiments. So in principle it works, but of course it has to be improved to make it really reliable. And one question is, of course, what are the dose response curves look like for the sequence of pulses? And we did a model study with 4 different mathematical models. I will not show equations. The Alif-Panfilov model, 2 variables, Mittel-Schäfer, 2 variables, Fenton-Karma 3, and BOCF, it's a 4-variable model. You see here typical snapshots of the chaotic dynamics. And now you can apply pulses. Now, if you apply only a single pulse, then the success rate, which is color-coded, yellow means high success, is a function of the amplitude. Here it becomes yellow, maybe it's not easy to see, but, and of course it's not a function of the pacing frequency, because if you have only 1 pulse, there is no frequency. But if you go now to 5 pulses, then you see a different picture. You see here it becomes really clearly yellow for these amplitudes. We have a high success rate. But on the other hand, if the frequency of the pulses, so the time separation between the pulses, is changing, then we have a low success rate here in the top. This is given here as a ratio of the pacing frequency divided by the so-called dominant frequency. Dominant frequency means you take a Fourier spectrum, you look for the largest peak, and the frequency of that peak gives you an estimate of the dominant frequency, a typical time scale of the system. If you use 10 pulses, you see a similar picture, but you also see that some additional peninsula is forming here, which becomes even more pronounced in case of 20 pulses. So this means we have a high success rate here in this region, which is good because it's with low amplitudes, but of course you have to know exactly the right range of pacing frequencies to make use of this. And if you look at this from the point of view of those response curves are just cross-sections here, because they show only the dependence here on the amplitude for a given pacing frequency, which is indicated here by the dashed lines. And then you see, if you go through this one here, for example, you go here, then you have a high success rate, but then it drops, comes very low again, and then it increases. And this is a typical behavior that you see in all the models we study. So we have these high amplitude, these high success rate peaks, but they are very, you have to know where to find them in the parameter space. And this means this depends very much on the proper choice of the pacing parameters. And this is crucial. This is, from a practical point of view, not a good situation, because in numerical simulations, we can compute such a diagram of the parameter space and then go to the right spot. In a clinical application or even in an experiment, you can't do this. You need something which is simpler, more robust. And that's why we came up with the idea to use non-equidistant pulses, not equidistant in time, to cover a frequency range. So again, this is the Fourier spectrum of an ECG signal, for example. The black line here in the middle, this is the highest peak. This is the dominant frequency, which was used so far to define the time interval between the pulses. So the inverse of the dominant frequency was used as an estimate for a good timing for the pulses. Okay, but now we want to cover a broader part of the spectrum because it has, of course, more information than just the dominant frequency. So we consider frequency here as indicated here by the red lines. And then the highest frequency, its inverse, is a short time interval, and the lowest frequency is a longer time interval. In other words, we have now a sequence of pulses which come slower and slower and slower. It's a deceleration pacing. And we use this now to control the system. Here it's again the idea, and to be more specific, you can compute the integral of the spectrum. This is this curve, it's monotonously increasing. Then you introduce a number of levels. If you want to have 10 pulses, then it's 10%, 20%, and so on. And this translates to frequencies. And these frequencies are then used to define the time intervals. It's a very simple recipe to do this. And it's adaptable because it starts with an ECG signal that you have measured and its Fourier spectrum. And it has only 2 frequency parameters, the cutoff frequency when you stop here, and then, of course, the number of pulses you want to use. This means it's easy to implement and to use in experiments, and we do this. And I want to show here some numerical results. These are dose response curves now for pulse sequences, and the green curve here, maybe you can see it, there is a green curve here. This corresponds to this adaptive deceleration pacing. This curve here is a single, this is a single pulse. This one here is, with a peak here, is from using equidistant pulses. So you see this deceleration pacing has a very nice dose response curve because it starts very early with low amplitudes, and then it increases and goes to 100, and that's it. And we found this also in other models. And we are now testing it in animal experiments, and it works quite well. Okay, so far about controlling with pulses and sequences of pulses. Now I want to say a few words about transient chaos in cardiac dynamics, because the state of chaos or fibrillation is, at least in simulations, you can see this very clearly, it's very often transient chaos. Just to illustrate this is a simulation with a phantom karma model. You will see in a moment when I started, your spiral wave dynamics, complex dynamics, but after a few rotations, and I made the movie short, you will see that the waves go to the boundary and then it's over. So it's self-termination. We do not apply any pulses, any shocks or so. We just run the system and it stops. And this is not only observed in numerical simulations. On the left, you see an experiment with a rabbit heart in a perfusion system. Again, we do optical mapping, so the colors that you see are the voltages on the surface of the heart. And if I start this, you see a complex pattern going back and forth, and you see here also some electrode signal. And then at some point, it stops by itself and goes to the normal heartbeat, and that's it. So it's a clear case of transient chaos. You also see this in 3D simulations on a realistic geometry, for example. Here you see these scroll waves, and they look quite complicated, but again, if you wait long enough, they go to the boundaries, and then you are in a quiescent state, and the normal heartbeat could start again. To describe this behavior, typically you want to know the average lifetime of the chaotic transient. And to understand this, or to estimate this, you should start different initial conditions in simulations, of course. In this case, 3,000 different initial conditions with a phantom karma model, which was also used for the previous movie. And then you ask how many of them are still chaotic. If time is progressing, you see the number of trajectories which are still chaotic decreases exponentially. And this exponent here, kappa, is called the so-called escape rate. Because in the state space of this system, you have a chaotic saddle, a fractal set, and the dynamics takes place on this, basically close to this chaotic saddle, but at some point it escapes from the saddle, because the saddle, like a saddle point, but this is a more complicated object, has not only attracting direction, but also at least one repelling direction, and this kicks you out, and the trajectory goes then somewhere else to another attractor. And the inverse of the escape rate, this parameter here, is an estimate of the average transient lifetime. And in spatially extended systems like this, you often find that this transient lifetime increases, in fact, exponentially with the system size. Okay, so, but why is this phenomenon, which is more maybe interesting from a theoretical point of view, why might it be interesting or even relevant for cardiac dynamics? Well, transient events and self-termination of fibrillation have also been observed in patients who were at the hospital. And of course, this can have many reasons, but one reason could be that it was really transient chaos. And the crucial question is here, how long is the transient time compared to the time you can survive in the state of fibrillation? If you know my chaotic transient is 3 seconds, and you know I can survive 1 minute, then you don't have to apply a shock. You just wait the 3 seconds and then it's over. If you know my transient time is 10 minutes, then you have to apply the shock. Otherwise, there's no hope. Okay, so the question is, can we predict the length of the chaotic transient, its duration? And the answer is no, at least not yet, at least not to my knowledge. What you can do, you can predict the average transient time in a system if you take into account other observables. But again, it's the average time. It doesn't help you to make a statement about the situation in which you are at that moment. And you can also study the impact of external perturbations on the transient time, and you find that the impact changes long before the end of the transient, typically 20 spiral rotations or so. And this might lead to another approach to estimate the length of the transient, but I'm not sure. This is work in progress. But there's one aspect, and this is what I want to emphasize now. If really transient chaos is responsible for the cardiac fibrillation, then this has implications for our ability to terminate it with low energy. And to discuss this point, I want to compare persistent chaos on the chaotic attractor and with transient chaos. Now, if you have persistent chaos, you have a chaotic attractor, you have a basin of attraction, and if you want to go away from this attractor, you have to kick your system or the state of your system so much that you end up outside the basin of attraction. Because if you, and then it goes to the desired state, maybe this one. If you kick it only a little bit, then it will go back to the attractor where you don't want to be, the fibrillation attractor in this case. So this means we need a minimal perturbation strength here to control the system. Now, if you have a chaotic transient, you have this chaotic saddle, there is no basin, there is no, and that means if you are here, for example, and if you do nothing, the system would need some time to go around and then go to the desired state, end of the transient. But if you kick it a little bit, and this arrow is quite long to make the drawing here, you can hope to go to a neighboring trajectory, which has a much shorter path to the desired state. So termination is much faster. And the interesting point is that there is no minimal energy needed here, and you can in principle use rather small perturbations. And this is illustrated here in a simulation, again with the Fenton-Karma model. You see here on the left the evolution of the perturbed system, and this is the unperturbed system for comparison. You see here the voltage, the average in space of the voltage is a function of time. And when I start the movie, you will see in the beginning both do the same until the moment when we apply the perturbation here. The perturbation will be only at 3 points. It's really a minimal perturbation. After that, they behave still similar, but then the perturbed system goes to the resting state. So here comes the movie. Now we go to the moment where the perturbation takes place here, and then you see the evolution, and then this one dies out. So in this case, this minor perturbation, low energy, so in some sense, already terminates or leads to a neighboring trajectory, which terminates much earlier. And of course, here the question is, how can we find these perturbations? Here we did a brute force approach, numerical simulation. We used the method which was developed by Cornelius and other colleagues for control of neural networks. So just to demonstrate that this is possible. In practice, you have no time to play around and to do this. So we need, of course, better methods. Then you can ask yourself, okay, what determines the transient lifetime? I want to make it shorter. I want to have the period of fibrillation much shorter. So what does it depend on? We looked at the role of heterogeneities, conduction heterogeneities in the medium. So far, I showed mainly simulations with homogeneous media, which is, of course, an ideal case. And we found that the average transient time increases drastically, because this is a logarithmic scale here, with a density of heterogeneity. So it's an exponential increase. So in other words, if you add heterogeneities, transit times become longer, much longer. We also looked at what happens if we add to these simulations, which are so far purely deterministic, if we add some dynamical noise. Again, we find, and this is work in progress, but it's a clear result already, that the dynamical noise also increases the length of the chaotic transients. So perturbations, noise, they all go in some sense in the wrong direction. They make the transit longer. So the question is, how can we shorten these episodes of fibrillation? And one approach which is so far quite promising is the use of delayed feedback, localized delayed feedback. The idea is quite old. We did some work almost 20 years ago on this. So you have a spatial temporal system, you have some sensors, you use the information from the sensors in a feedback control loop, and then you apply some control signals over here. And if you do it in a proper way, you can manipulate the spatial temporal dynamics. In our case, we do the following. We took the Fenton-Kammer model and other models, and here is a snapshot of the dynamics. We introduce here such a control cell or control unit of a given size. We compute in this unit the average membrane voltage and divide it by the volume, by the size of this control unit. This is our signal at control unit I. We use this signal now to set up a control signal with delay. So this is the signal at time t, the signal at time t minus tau, with some factors, Ka and Kb, which have to be chosen properly, of course. And then we use this current at cell I to implement the stimulation current density in this cell, given by this expression here. It's basically this current divided by the volume again, and it's only active in the cell. Everywhere else it's zero. And this current density is then added to our differential equation for the membrane voltage, diffusion term, the other ion currents, and this is our additional stimulation current. Okay, so here are the equations again. So we do this, of course, not only in a single location, but we cover our region with many of these control cells. And so there is a unit of control cells with a spacing of G. And now we have three control parameters, the delay time and the two prefactors, Ka and Kb. And those of you who remember a little bit about chaos control, of course, may say, oh, this is Piraga's control, isn't it? Well, it's not exactly, because we do not assume that the size of them are similar, and we do not assume that they have a different sign. If you assume this, then you have the famous formula for Piraga's control, or time delay autosynchronization, which was introduced in the 90s by Piragas, for example, to stabilize unstable periodic orbits in a chaotic attractor. This is not our goal. Our goal is to make the transients shorter. But in fact, this approach, Piraga's control, has been used also to stabilize unstable spiral waves. So it could be applied also in this context. Okay, so here is now our setup again. And what we do now is we vary the spacing of the control units. So this is the spacing. In other words, we vary the density of control units. And then for each value of the spacing, we compute optimal control parameters. Optimal control parameters are, of course, those who make the average transient time shortest. So this T DFC is a transient line with optimal values for the control parameters here. And then you want to compare this to the case where you did not control the system. This is this T reference. And one way to compare it is to compute the reduction, which is 1 minus the ratio between both of them. If the control with optimal values leads to transient times very close to 0, then the ratio, this reduction number R, is equal to 1. If you have no progress, if both numbers are basically the same, no progress with respect to the reference, then this is 1, and 1 minus 1 is 0. So you want R to be close to 1. And then, of course, the more control units you take, the more you can control the system. So you want to see a kind of efficiency of the control elements. This means we consider the reduction and subtract the control unit density. And the idea is to see the best compromise between the number of control units and the transit time reduction we can achieve. Okay, here is a result. So you see here, this is the mesh spacing. Low number means we have a very dense covering with these control units. And you see then, if it's very dense, then the blue curve, which stands for the reduction rate, which is defined here again, is of course rather high, and it decreases if we use less and less and less control units. This is what you have to expect. The green curve is the efficiency, and this curve increases, has a maximum at 9, somewhere here, and then it decreases. And the maximum of 9 means in this simulation 64 cells, just to give you an idea. If you use only one control cell, you still have a reduction of 10%. And this is already, this works a little bit, but of course not sufficient. Now, what are the mechanisms which lead to the reduction of the transient times? We found that there are basically two mechanisms, and if you have a large mesh spacing, this situation here, large compared to this one, then you see if you analyze the dynamics, that there is an acceleration of the wave fronts motion, that you create a lot of short-lived singularities, phase singularities, new spirals, which is maybe a bit counterintuitive because you think, I want to get rid of the spirals. No, you create new ones, but these new spiral waves, they annihilate each other very quickly, and this leads then to the observed reduction of the lifetime of the chaotic state. In the case of a small mesh spacing, this one here, you basically simultaneously hyperpolarize the whole medium, and after that, it basically the wavefronts go to the boundaries, and the dynamics is over. This is, of course, not so interesting case because you don't want to cover your system with many of these cells. This is more interesting. Now, what happens if we change the domain size? So far, I showed you simulations with a domain size of 80 by 80. And if I change the domain size, then the transient duration increases exponentially without control. This is the red curve. It's a linear curve here because we have here a logarithmic axis. But this is the result I mentioned already in the beginning. These transient lifetimes and spatially extended increases exponentially with the system size. Now in green and in blue, you see the curves we obtain with the two cases of control with a large mesh spacing in green and a small mesh spacing in blue. Of course, small mesh spacing, which means a lot of elements here, leads to the strongest reduction, but also the other case where we have only 64 elements in the case of size 80 by 80, leads to a significant reduction because these are really magnitudes from 10 to the power of 3 to 10 to the power of 6 or higher. So this also shows up here in this curve showing the reduction R I introduced as a function of the domain size. It increases here and approaches 1 quite quickly. So in other words, with the increasing domain area, the approach I showed you with the local control elements becomes more and more efficient and can reduce the chaotic transient lifetimes with very high percentages, approaching 100 here. So this is a promising approach to reduce chaotic transient lifetimes. Now let me come to the summary. I first talked about the heart. The heart is a network of electrical and mechanically coupled excitable cells. And it's an excitable medium. This is important because this means it supports not only the propagation of plane waves, but also spiral waves and spatiotemporal chaos. And this is underlying the state of cardiac fibrillation, which is very dangerous and has to be stopped immediately. You can study it experimentally, for example, using optical mapping or high-speed ultrasound. Actually, there are other techniques nowadays. You can use genetically modified cells and use optogenetics techniques where you shine light on the cells to induce excitation. I didn't talk about this, but this is also experimentally a very interesting approach because you can do things that you can't do in the electrical domain. And we can control it. Yes, we can control it by sequences of weak pulses because it's a chaotic dynamics. It's very susceptible to any perturbation, but you have to apply, of course, the right type of perturbation to achieve the goal to terminate it. And this brings us to the idea of low energy defibrillation using not so strong shocks. And in particular, the approach I showed you with this adaptive deceleration pacing it seems to be quite promising. Then in the last part of the talk, I talked about the role of transient chaos. And we saw that for conduction heterogeneities, for example, I mentioned they increase the transient time, noise increases the transient times. We want to make them shorter because we want, if we can reduce this transient time, it's similar to a defibrillation. You go back to the non-chaotic or non-fibrillation state much more quickly. And one approach which could be interesting also in experiments and in applications is the use of delayed feedback control, because in simulations it showed a significant reduction of transient times. Of course, and this is my last remark here, we talk here about transient chaos from the point of view of the dynamical systems. We consider the heart as a stationary system in these simulations. In the real world, the situation is more complicated because if you are in a state of fibrillation, there is no oxygen supply. The heart itself changes its dynamics, it becomes ischemic, and these changes in the system have not been taken into account here, and they could also lead, of course, to a termination. So distinguish these effects on different timescales is, I think, an important point which is still on our list. Okay, so this is my last slide. Thank you for listening, and I want to thank in particular Stefan Luther, head of our group, and also Thomas Lienkamp, who is now professor in Nuremberg, and all the other members of our research group. I didn't list all the names because I think most of you don't know them, and also our clinical partners, in particular at the University Medical Center in Göttingen for collaboration. And I thank you again for your attention. Thank you.
Thank you very much for your presentation, sir. Any question, please? Yes, please.
First of all, thank you for the very interesting talk. I have two questions. First, you mentioned the model for the spiral wave and the exponential intensity, right? For initial conditions, and then we try to class is possible to predict the duration of the adaptant. Why would this even make sense if the distribution is exponential in sequence? I remember we have said if the system doesn't remember, doesn't know what it is. So what do we expect?
The distribution is one of the I showed a number of trajectories which were spherical and which was decreasing exponentially. Yeah. So this is for the average of 3,000 realizations, 3,000 trajectories. So a few of them, they terminated very early. And of course, we could find out that that we have this great risk Germany within the next 10 years or so, then we don't have to apply the shock. I mean, it's very short together. There are a few cases in the average which are very short. We don't identify them.
So if you go back to the initial conditions that generate these shock-free events, are they scattered throughout space or clustered somehow?
Yeah, that's a good question. And, you want to classify them from the beginning, in a sense. Maybe this is in the future possible using machine learning or so, but even if you're looking in very much more simple cases like that, you know that, so you are mentioning you can also have transit care there, and there the initial conditions are just enormous. But if you then make the diagram, take the initial condition and make it a color according to the diagram, you can see a very colorful picture with a lot of fine structure. In other words, the initial conditions which are very close together can have very different transit times. So it's very
That's another question.
Yeah.
So, you didn't touch the question of addiction. Very important. So, from the image that you presented initially, was like this spatial synchronization. I would expect that if there was like lag, there was some using this synchronization, can sell essentially one stage. So maybe like through yes, and you see that this is using synchronization. This one of the lag is just ecstatic. We know this can be used as
Yeah, I think what I didn't talk about here was the idea to use machine learning and other techniques to predict temperatures in videos. It's possible, but then again, you can do this in simulations. You generate first a lot of training data, train your favorite algorithm. It can predict for some time problems here, you cannot do longer. But then, how we can translate this to the real world situation? We don't have that training. And if the system can be used as a combination of different parts, or sanitation part changing from day to day, then the models that learn, sophisticated models, you can reproduce as a mistake. That means a picture. You can do this in principle, but it's an issue of training.
Thank you very much.
Any other question? Oh, yeah.
I mean, the previous one, so when I go about one, say the same. I took a little bit of first of all, we talked about the control. And you mentioned pulses, high pulses. Should these pulses be synchronized with the heart somehow?
There is no heartbeat anymore. In the state of fibrillation, you don't see a heartbeat. Remember the diagram I showed in the beginning. There was a heartbeat, a normal heartbeat. But then there was this oscillation, okay, the cardiac started. And in the case of fibrillation, you have a completely irregular signal. You don't see a heartbeat.
I mean, not the actual signal, but so when there's a heartbeat, there are different intervals between the heart beating pulses. Should this be somehow connected to that? Your sequences of pulses.
Yeah, this is, I mean, okay, we try to connect it to this idea using the dominant frequency. Because if you have a heartbeat, you have a clear dominant frequency, and then you use the inverse to define the time intervals. But if you have a really strong fibrillation, you have a broadband spectrum. And then that's why we came up with this, considering the range of frequency with this deceleration. I'm not sure that answers the question.
Yeah, and that's the question about this persistent counts and transient counts. So you said in order to control one of them, you should apply large pulse, let's say, in order to get out of space.
Yes.
In order to control the second one, it's enough with a small pulse. But how to distinguish that? how do you know is it the transit chaos or is it the real chaos?
Philosophical question. Because you work through the eye. In the numerical simulation, in principle, you can't distinguish. Because at some point you have to stop the simulation. And at that moment, you can still be careful. But you don't know whether you terminate maybe a few seconds later, but you stop the simulation. So there's always to distinguish this or to classify this is not that easy. If you have a set termination, then you know what's going on. If not, we don't know yet whether it's persistent forever or just a very, very long improvement.
But it's not possible to detect that meanwhile you're looking at the signal itself.
Never say never, I don't know. But it's difficult. We are operating in principle infinite dimensional state space because these are functional questions. And we can identify the structures which differentiate invariant manifolds and things like that. But again, we can achieve this in study with a lot of computing power. In experiment, we don't have the time and the data to decide.
So to be sure, you're just applying the largest possible distance.
No, yes. No, exactly. This would be what the microbiota has to do to be sure to save the life. But we would try to use weaker hypotheses and see what happens. And then we have to have a better hypothesis. If this is not successful, then
Thank you.
Okay, you guys, thanks one more time.
Thank you.
Okay, good morning everyone, and welcome to our special track session, Complexity in Medicine and Pharmaceutics. It is my pleasure to introduce our first speaker, Dr. Konstantinos Gardikis. Dr. Gardikis is the R&D Director at Apivita and Professor at Frederick University. His presentation is entitled Matter Complexity, Nanotechnology and Regulatory Framework from Medicine to Cosmetology. Dr. Gardikis, the floor is yours.
So, good morning. Thank you very much, Yannis, for the kind introduction. First of all, let me express my gratitude for the invitation towards all the organizing committee and especially Professors Stavrinidis and Professor Demedzos. So, in today's talk, I will try to identify some very known and very specific gaps on the way to characterize and ultimately, which is the most important for industrial developments, to regulate nanotechnological developments concerning all medical and paramedical fields, especially focusing today on nanomedicine and nanocosmetics, but the same applies for medical devices, same principles at least, for medical devices, for food supplements, anything dealing with the connection between human health and new technologies, novel technologies such as nanotechnology. Okay, let's wait. I will divide the presentation in three specific parts. One is a brief introduction to what chaos theory brings to the characterization of complex matter and such as nanotechnological developments. Most of this is widely known to the audience of this symposium, but I would really like to connect this theory, this information, with pure industrial development and ultimately with regulation. Then we will go to the regulation part. You can change to here. Then we'll go to the regulation part first of nanocosmetics. And why first of nanocosmetics? Because taking it from a pragmatic point of view, it is a field that allows, due to looser regulation, more easy development. So you will see that in nanocosmetics, in the cosmetic industry, actually applying nanomaterials as bioactive components, you will see many different kinds of nanomaterials. Many of them are not present in pharmaceutical developments, only in a research state. Then move to nanomedicine, and finally conclude the link between the obvious gaps of regulation, which is of course due to the limited, the linear, we could say, perception of such materials. So the link of this obvious gap with developments that have been going on that step on dynamic systems characterization, such as chaos theory, that may conclude at some point to a much broader, a much more specific way to characterize, to assess safety, efficacy, stability, and general properties of nanomaterials in medicine and in cosmetology. That would be rightly an outcome of a very specific and very contemporary and innovative regulation. Okay, let's allow a few seconds for a quick restart. It's okay. So, as we said, let's begin by some fundamentals of nanotechnology in systems that address to the human biology. So we all know that complex systems are those systems that behave non-linearly. We're dealing with small systems whose thermodynamic profile affects their effectiveness as delivery systems, as carriers of bioactive materials, and whose thermodynamic behavior deviates from classical thermodynamics. Systems whose size diameter is smaller than the range the interaction of forces acting on the system itself. So as very thoroughly presented and in a pioneering way from Professor Demedjos in the Nanotechnology Lab of the Nanotechnology Lab of the Pharmacy School of Athens, the surface properties that arise from the self-assembly of those substances that make up supramolecular structures is not identical from one product to another, and more interestingly, they cannot be identical from one batch to another. This inherent, let's say, flow of nanomaterials, that is, of course, due to the chaotic nature of those materials, plus the very complex, the complexity of the process that is needed in order to do such developments and more and even more complexity to scale them up is by default the major regulatory gap. As you may know, regulation wants things to be similar or as similar as possible in order to be able to guarantee safety and efficacy. Safety for cosmetics, safety and efficacy, of course, for medicines. Of course, this non-reproducibility directly marks a regulatory gap that concerns safety and efficacy, of course. The complexity characterization, the characterization of such complex systems, of course, utilizes many tools, many, let's say, traditional and mostly linear tools that we have in our disposition to this moment. So we can measure the composition, residual substances, ratio of drug to carrier, bioactive substance to excipients, physicochemical properties, with most importantly the size distribution and charge of particles, which is of course very essential, but does not ultimately determine the fate of such systems in the human body. Polymorphism phenomena, morphology, stability during storage, but very importantly, stability during administration, at the time of administration and after administration. Remember, we are talking about highly dynamic systems. So when are we assessing the stability or the size or the charge? All those parameters are parameters that change over time and according to the environment, of course, and in vitro release. Of course, the complexity of those systems is driven by much more phenomena, such as surface area to volume, which is something that is required by regulation in medicines. It's not required in cosmetics, and this creates a lot of questions. Dynamic aggregation and agglomeration phenomena that are very hard to assess. Interfacial chemistry phenomena such as charge, such as hydration, cell influence, that influence stability and biological interactions. Biocorona formation, the absorption of small molecules or macromolecules, mainly in systemic circulation, that alter fundamentally the nature of those systems and, of course, their behavior and their identity. And the assessment of processing history that gives a direct energetic output to the system, such as mixing energy, pH, ionic strength, temperature, that, of course, ultimately change the performance of those systems. So we're not discussing about materials, we are discussing about a whole system that comprises formulation, environment, time, and, of course, energy. So let's start by the nano cosmetics. We have nanomaterials in almost every application of cosmetics known, from aging to hydration to sun care to sun protection. We have, according to the regulation, two major types of nanomaterials in cosmetics. The unstable nanomaterials, the ones that disintegrate upon interaction with the human skin. For example, liposomes, nanoemulsions. Very interestingly, for the regulation, these are not considered nanomaterials. They are nanomaterials, of course. A liposome of 80 nanometers is by default a nanomaterial, but for the regulation, it's not it's not under the nano regulation, at least for the European Union and the FDA. Same goes for the two major regulatory bodies. Why? Because these systems normally disintegrate upon interaction with the human skin. And the other major category is insoluble nanoparticles, mainly titanium dioxide and zinc oxide. Also fullerenes are used in a wide extent, that are highly regulated because they are considered biopersistent. Okay, and the uses in cosmetics are two very basic categories. One is sun care, so nano sun filters, very important category. Let's remember that in the USA, sun care, the sunscreens are considered medicines. They are under the OTC, over-the-counter regulation, so it's fundamentally a very important field that does not have to do only with beauty, but it has directly to deal with health. And the other category, very major category, is delivery systems, that most of them are not regulated, at least by nano regulation for the European Union. You can see developments on the market: novasomes, nanocapsules, nanoemulsions, nanosomes, fullerenes. Practically there is L'Oreal has over 600 patents, on one example, on nanomaterials for cosmetics. So it's a huge field. Why? Because you saw that many of these are not regulated under the very strict nano regulations. And the manufacturers, you will see all the major players. Okay, so some very basic things about the regulation to move on to what is very I think the interesting part of this session, which is the regulatory gaps and how they can be addressed by contemporary theories in physics. So let's not dive into the cosmetic regulation. It's beyond the scope of this talk. Let's focus on what has to do with nano developments. So determination of the safety of the ingredient is the ultimate fundamental. What does safety mean? Safety means that a final cosmetic product, a cream, a shampoo, whatever, is safe for human use under normal and foreseeable conditions. This is the fundamental of the European regulation. And what does safety stem from? It stems from safe ingredients. So we're going back to ingredients. So if we have nano ingredients, we have to make very specific assessments, as in all ingredients, probably except the grass, that generally recognized as safe materials, where they can pass by, let's say, by literature data. For example, if you have a chamomile extract in glycerol, you don't have to do all the things that you will see in the next slides. And they're responsible for this assessment, for the safety assurance of those products on the market, is the responsible person, meaning the manufacturer, the distributor, whoever legally is the responsible person. So, dealing with nanotechnology, there is a field in the regulation that very, very briefly and with many gray zones, of course, describes what a nanomaterial is for the EU cosmetics regulation. It's an intentionally manufactured, very important, intentionally manufactured. So if you take an exosome, for example, from from a plant, which can be a very, very nice nanotechnological compound, a natural one. It doesn't fall into this definition, okay? So it's not considered nano. Insoluble or biopersistent, very interesting also. This is why we said nanoemulsions, liposomes do not fall in this category, with one or more external dimensions or an internal structure on the scale of 1 to 100 nanometers. Of course, anybody familiar with nanotechnology can identify 1,000 gray zones and question marks in this definition. I will not elaborate on this, but one has to keep in mind that the EU cosmetics regulation, let's stick to the European Union, okay, because FDA has different modes of addressing it. China is a totally different story, etc. For the EU regulation, that is more interesting probably to most of us here. Let's remember that cosmetics are regulated by the EMA, by the cosmetics regulation of the EMA, of the European Medicines Agency, but also falls under the REACH regulation, which is a horizontal regulation for all chemical entities in the European Union, from plastics, oil developments, whatever, to medicines, to everything. So the REACH follows a very different, much more thorough, let's say, definition for nanomaterials recommended at least by the European Union Observatory for Nanomaterials, the UON. We're not going to elaborate on this just because a totally new cosmetics regulation is about to be in force in 2027 that, as we have understood, will be much more thorough on this. So this ambiguity will very soon change. But let's stick to what's happening for the moment. So for the moment, we have several articles that deal with the assessment of safety of raw materials in general, and we have very specific paragraphs for nano that states in the Article 16 that one, which is very unique to nanomaterials, doesn't happen with any other cosmetic materials. A manufacturer, a producer, a developer has to notify the European Union on nanomaterials that will be placed in a cosmetic product 6 months prior to the entrance on the market. So the European Union and very specific bodies of the EMA have 6 months to raise any questions, and there are usually a lot of questions, on the safety, purely the safety. They don't deal so much with efficacy because it's mostly beyond scope in most cases in cosmetics, with the safety of such materials and definitions that concern toxicology and characterization. Also, if you see the INCI list, so the names, the chemical names of the substances in cosmetics, if there is a nano, according to this regulation, it will be in brackets after the name of the substance. So if you see titanium dioxide, brackets nano, it's a nanotechnological form of titanium dioxide. So by this, kind of cleverly, because we will see in the next slides that there is, of course, a regulatory gap that concerns also safety and, to a point, efficacy of nanocosmetics. Same goes to a lesser extent for nanomedicines as well. It throws the ball to consumers to see that, okay, there's a warning, there's nano there, could penetrate could go into your systemic circulation. If somebody is aware of this, just notifying. So this is what happens for the moment. So for the toxicological requirements for raw materials are very specific. It's a wide array of assays that have to be done to prove the safety of materials. Some of them, we're not going to elaborate on this, but some of them are, as anybody can understand, are rather tricky for nano development. So dermal and percutaneous absorption, very hard to assess. It's easy to assess with in vitro assays, such as to do France cells assays or such, but in actual, in live, in human conditions, it's a difficult story also to assess possible systemic penetration, repeated dose toxicity, and toxicokinetics. All these fields are rather tricky. There are very, for the existing, for the nanomaterials that are on the market, but actually for the majority refers to nano titanium dioxide and nano zinc oxide. There are very specific properties that are required. There are explicit specifications from the EMA in order to be able to incorporate them into cosmetic formulation. So there is a maximum concentration, and there are specifications for size distribution, sometimes for charge in zinc oxide, for coating, for aqueous solubility, etc. One may find them in Annex 6. Of course, there are these requirements for toxicology, for characterization, but the general notion, so what EMA starts as has as a starting point in discussing those nano-cosmetic developments, is that a priori, to begin with, a nanomaterial is potentially harmful, so you have to prove that it's not harmful, and it obliges manufacturers, and this is, of course, very correct, to assess the whole nanosystem rather than the encapsulated molecule. So the toxicology, the physicochemical properties, etc., have to deal all. EMA doesn't care for the encapsulated substance as long as it is, of course, compliant, it has an inky name, etc., but it refers to the whole particle. Of course, we can identify some very specific limitations in the regulation to this moment. We don't have sufficient information for hazard identification, for exposure assessment. Remember, cosmetics can interact with mucous membranes in the nose, in the mouth. Imagine also in these industries there are people working that may inhale to large quantities also, nano titanium dioxide, etc. So we're not thinking only about consumer, we're thinking about the whole process of nanocosmetics. Cellular uptake, that is a very big question mark for nanocosmetics. Physicochemical parameters that governs absorption through membranes, physicochemical parameters that govern accumulation in secondary organs upon systemic delivery, finally, of those materials, which is rather something that has been proven to be happening for some developments, transport of the nanoparticles across the placenta to the fetus, etc. So to move very briefly to nanomedicine, let's keep in mind that we're moving from a regulatory logic of safety to a regulatory logic of risk-benefit, quality, safety, and efficacy. So different mindset, and from data emphasis on exposure, local safety, skin safety, and product characterization to CMC, to chemistry, manufacturing, and controls, quality, non-clinical, and clinical evidence. So I will, skip this part. We know the nanotechnological developments where they focus. So they focus on diagnostics, on regenerative and therapeutic concepts, and very mainly on drug delivery, either for reformulation, for more safe and effective use of existing molecules, to oncology, a very fundamental field, and vaccines, of course, that is a very known application to all. There is no concrete nanotechnology approach for the EMA, for the regulation. There is no standalone nanomedicine regulation. We are using the existing medicinal pathways for development and regulation, plus very specific nano-relevant guidance. There is guidance which is nanoparticle specific for intravenous iron-based nanocolloids, liposomal products, block copolymer micelles, surface coatings for parenteral nanomedicines, and there are constantly guidelines and reflection papers on the EMA on the non-biological complex drugs system all the time, of course, with a logic of CMC quality, non-clinical evidence, and clinical evidence. So if we go to the gaps, we can talk for ages on the gaps on the regulation. These are things that are very well described also in the literature, but they span from possible genotoxicity to also unknown and increased, but to a large extent unknown cellular uptake, the protein corona phenomena, so what happens actually in the bloodstream when a nanoparticle enters, to possible environmental impact, and very fundamentally a lack of a harmonized regulation, concrete harmonized regulation across regulatory bodies in the world. So these gaps they paint very specific regulatory unmet needs, such as the need for a clear definition of nanomaterials and better understanding of their unique properties and more interestingly, interaction with the complex biological systems, the establishment of a harmonized nanotoxicological categorization classification system, the huge issues of scaling up. So in vitro, we have some very good results, batch-to-batch reproducibility in lab scale. When we go to pilot scale, things begin to behave differently. When we go to scale up, it's very hard to keep the consistency of physicochemical parameters. Reproducibility of batch to batch, and the issue of nanosimilars, of course, where composition, which is of course very important, plays so little role in the actual fate of those materials inside the human body. So, to conclude, what can chaos theory actually add to this help in bridging the gaps between reality of nanotechnology and the flawed, let's say, the generally recognized as flawed regulation at this moment? Why chaos theory is important? Because it addresses non-linear biological systems that are very highly sensitive to small changes, something that linear logic of physicochemical assessment, clinical assessment, and regulatory does not allow to follow. We have identified very specific limitations of traditional models that fail to capture the complex nanoscale interactions with biological systems. The probabilistic and adaptive models of contemporary theories, as chaos theory, may adapt to variability in biological systems and give us the tools to monitor those systems very close to what is actually happening to them and what they do to the human body, so the whole pharmacokinetic and pharmacodynamic behavior. And ultimately, besides regulatory, addressing all this complexity will definitely lead to improved nanomedicine design. So we already have tools. It is a matter of systematization of those tools, of casting specific standards that will of course, slowly and upon validation, can and will be adopted by regulatory and have very specific guidance for the industry in order to be able to produce safe and effective developments that rely on novel nanotechnologies. So contemporary biophysics, of course, thermodynamics, very interestingly, that are not used by the regulation at this point. So small system thermodynamics that may address very small fluctuations, very small changes in such complex systems and transitions between metastable configurations, which is extremely important for the characterization of the fate of those nano developments, and ultimately fractal geometries that can assess the chaotic dynamics and that classical geometry and classical physics definitely misses for those systems. And all this added up together in a stabilized, in a concrete form, definitely leads to solving, at least to a large extent, the issues of stability, reproducibility, and performance that are the major issues of nanotechnology. To conclude very quickly, we're talking not about small materials, we're talking about complex, chaotic systems where interfaces, history, environment, and energy matters, things that are not assessed by regulation at this point. Complexity concepts, from non-linearity to emergence to multi-scale behavior, are directly linked to nanosystem science, and adopting a mindset, first of all, and then a set of regulations that complexity is intrinsic in those systems and not just an exceptional phenomenon, is apparently the only way to drive, first of all, safety, efficacy, stability, and the future of those systems, and of course, more innovative, more safe, more effective developments from the part of research to development to finally the patient, of course, which is the ultimate goal of all those developments. So thank you very much.
Thank you, Dr. Gardekis, for a very interesting presentation indeed. I think we have time maybe for one question from the audience. Is there anyone that wants to ask anything? Okay.
Do you think that regulations will probably work will get to the point that will actually protect consumers? Sorry.
Yeah.
No. Do you think, sorry,
Again,
that
please.
regulations from, for example, the EU or the FDA are gonna actually get to the point of protecting the consumers and the people on the in the labs making these compounds? Because as far as like nanomaterials are concerned, because of their nature, we're not gonna get to a point that they do not get into the bloodstream, etc., etc. So how do you think they're gonna approach this problem and actually protect people?
Globally, the mindset of regulators and regulations is based on safety. So there is of course, the point of view is not harmonized, and this is a major gap in regulatory logic. For example, the FDA is much more. It used to be, at least, it starts to change since last year. It used to be much more, let's say, innovation-driven and focused on efficacy, rather than exhaustively demanding safety information and toxicological information. The EMA works the other way around. Of course, as you say, there are fields biological complex drugs, complex development, even biological drugs also, where we have a very specific lack of information due to lack of systematized tools to assess safety and toxicology. And what happens, and what in my opinion is the real gap here, is that it is every development for let's say novel therapies is so much case by case, so that it largely depends on the interaction of the developer with the regulator. I don't say that, I would never say, because I know from my regulatory experience with the regulatory bodies that this is something that will make exceptions for something like this. But I want to say that largely the fate of something novel as a development will depend on an interaction that goes on, and at some point, regulatory boards, this especially happens in the pharma industry, are convinced that what you're developing is safe. But of course, we are lacking the tools. So the goal of the regulatory is safety, safety, safety. From the moment that there are no absolute tools, there are two ways, or absolute ban. That is the case. If you see the files that are submitted to the EMA, even the FDA every year, it's like 90% of them they get cut because missing information. But still, them that have the adequate information miss some very important parameters, and so always the assessment is cost-benefit. An assumption of cost-benefit according, of course, to clinical, to evident non-clinical and clinical data at the point we are discussing about. We are very sure that adopting all those technologies that, of course, are not something, it's not a proposal that the regulators have never heard of. There's work been going on in all this field. In 10 years or in 15 years, we will have much more safe products on the market, and we will know it by design.
Dr. Gardikis, thank you so much. Thank you so much for your presentation. So we can move now to our next speaker, Dr. Maria Houdulesi. She's the Intellectual Property and Research Liaison Officer at Unipharma Pharmaceutical Laboratories, and also a postdoctoral research scientist at the Department of Pharmacy of the University of Athens. She will present her talk, Morphological Complexity of Liquid Crystalline Nanostructures, Formulation Aspects and Effects in Drug Delivery Technology.
Thank you, Yannis, for the presentation. Good morning to everyone. Do I have enough time or should I run? Okay, something intermediate. Okay. Good morning. I would like, first of all, to thank the organizing committee of the Congress, and especially Professor Demedjos and Professor Stavrinidis for inviting me to give this talk about how we can find the morphological complexity in liquid crystalline nanostructures and how the formulation affects this property and, in general, in drug delivery technology. As a start, lipids are amphiphilic molecules that have the property to self-assemble in water solutions according to their properties and give us different kinds of lamellar and non-lamellar mesophases. As we may see, there is a great variety of different mesophases and different grades of internal complexity in these structures. All these structures, depending on their internal mesophase, they can be further utilized to give us nanoparticulate systems, either liposomes or tubosomes or exosomes, etc. In this talk, we focus on the tubosomes and exosomes due to their high grade of complexity within their internal morphology, a property that give us maximum loading capacity and control drug release kinetic. Apart from internal morphology, these nanoparticles can be further functionalized via targeting moieties or polymers in order to have precise drug delivery, as we can see in the following slides. Through this study, we managed to have a development process from model liquid crystals to stimuli-responsive ones to liquid crystals by changing the stabilizers, eventually yielding to subcellular targeting and stimuli-responsive multifunctionalized nanoparticles of high grade of internal complexity. As a first step, we started by studying the complexity of model liquid crystalline nanoparticles by using typical used lipids and common stabilizers as poloxamer. And we studied the different formulation parameters like the type and the concentration of the lipid and the polymer and the preparation method. From that, we assessed that there was a different physicochemical behavior according to the formulation parameters. That was also assessed by static light scattering for the first time in the literature. Static light scattering indicated confined nanostructures with almost spherical shapes, and temperature-induced transitions to less compact structures when we had increased temperature due to increasing Gaussian curvature phenomena. All nanosystems were high stable over time, colloidal stability over time. We also found that they had reversible temperature-induced size decrease and structural changes as well as. And different interactions with serum proteins. They were quite prone to serum proteins disintegrations, that a disadvantage that we managed to control in the next steps. There were stable upon increasing ionic strength. And now let us go to the most interesting part, which is the morphological characterization of internal organization, reflecting the different grades of complexity within the structures, where we may see that according to the formulation parameters, we had a high grade of internal organization, like double diamond type symmetries that were assessed by that were assessed by Fourier transform, as well as some honeycomb motifs pointed out with orange that tend to hexagonal faces. Following to other concentrations and other weight ratios of phytantriol lipid, cubic structures were remained, and also from these figures we assessed also some phenomena of the interaction between lipid and copolymer. That is different when we change the lipid from phytantriol to glyceryl monolate. And in this type of lipid, we had also different kind of morphological categories. Apart from nanoparticles of high grade of internal complexity, we had two different types, either regularly ordered, with pointed out with red, also some others with irregularly ordered internal complexity that called us as sponges. The morphological characteristics were strictly dependent to the amount of the polymeric stabilizer. And as regards the exact categories, we may see that sponges, although they had such a disordered interior, they are very useful in order to have a dispersion of low polydispersity and a reproducible mean size and colloidal stability, because they need less energy to be consumed during preparation process. Moreover, some interesting phenomena were some fusion phenomena that we managed to illustrate via cryo-TM, that were fusion phenomena and vesicular cell coating phenomena that, although they seem that this fusion phenomena may tend to precipitation, contrary-wise, they can yield to crowded vesicular populations that further stabilize the dispersion, because this layer can act as material covering that keep them dispersed in the solution. These fusion phenomena are reflecting a dynamic formation process and a gradual transition from intermediate structures with varying degree of organization. Also, this process is the same process that happens also to our cellular membranes. We further studied the microenvironmental parameters via fluorescence spectroscopy, where we have different grades of micropolarity and microfluidity according to the formulation parameters. And as regards their thermal characterization, the enthalpy of the main transition was found to be independent of the polymeric stabilizers. However, it is strictly associated with the chemical structure of the lipid. So from this first part of the study, we saw that the formulation parameters are very strictly to the final complexity of the nanostructures. And this property is also affected by the environment. So as a next step, we took these model systems and we tried to upgrade them to stimuli-responsive ones by utilizing a stimuli-responsive blocopolymer that has an ionizable amino group that is protonated in different pH conditions. We tried different lipids and polymer concentrations to assess that there was a positive zeta potential due to the protonated amino groups. And some morphological reconformations that we observed during the pH-induced transition of the blocopolymer in acidic pH. The colloidal stability was also studied, and as regards the pH, we found a very interesting pH-dependent transition of the charge due to the PDMA polymer, which is very useful for further intracellular delivery of the nanoparticles, endosomal escape, and release to cytosol. Structures where we had also temperature-reduced alterations due to the polymer. Different kind of interactions with the serum proteins and ionic strength. And now, as regards the morphological characterization, we had also a structural variety of different kinds of morphologies and nanoassemblies and fusion phenomena. For example, very interesting nanostructure was this lamp-like shape. And when we tried to combine two different blockopolymers, we had different morphological diversity and different grains of complexity within the nanostructures. Also here we had cubic structures of primitive type along with some sponges. The microenvironmental parameters were prone to the temperature changes. While no differences were found as regards the transition temperature compared to the model systems. So, as a next step, we managed to have stimuli-responsive properties with changes in the polymeric stabilizer. And as a further step, we tried also to broaden the toolbox of the polymeric stabilizers with further polymers of different topologies and different architectures. And specifically a blocopolymer of polycaprolactone and a gradient polymer of polyoxazolene. Again, we tried different concentrations and different ratios. Both of polymers were chosen because of their high biocompatibility and their stealth properties. And we found that the physicochemical behavior were strictly related to the architecture copolymer. For example, when we have a gradient copolymer, there were more entry or exit points within the lipid bilayer. So there is a different packing mode of the lipids that yield to different physicochemical behavior, different structural behavior. Here it is the colloidal stability over time. We saw a reversible temperature-induced structural changes in both type of polymers. And also a different kind of interaction with the certain proteins. For example, the gradient copolymer managed to protect the nanoparticles from the albumin. And again, the most interesting part is the morphological characterization and the grade of complexity that was found to be strictly related to the architecture of the polymer and the combination with the lipid. For example, when we have the blocopolymer of polycaprolactone, there is a similar situation as in poloxamer model systems. For example, we have different type of cubic nanostructures along with sponges. Interestingly, when we increased the polymer concentration, some multilamellar striated nanostructures pointed out with green were found. That is an evidence of exosome formation. And when we changed the hydrophobic ratio of the blocopolymer, here it is a high polycaprolactone percentage, we have also the formation of some worm-like micelles that were not found in the previous systems. Here also. And now there is a completely different picture when we have changed the polymer from blocopolymer to the gradient polymer. Here we saw that the most intensive packaging that the gradient copolymer provokes give us a higher percentage in number also of the organized nanostructures. We have a greater number of cubosomes along with some multilamellar structures. Also in the highest polymer concentration, and also in combination of gradient copolymer with blockopolymers. So there is these highly packaged membranes are reflected also to the internal morphology and internal complexity of the nanosystems. As regards the microfluidity, we had a temperature-induced decrease of micropolarity, but increase of microfluidity. And this morphological behavior is also reflected in their thermal behavior, because in the systems of gradient copolymers, we saw that okay, we saw, this is the figure down, that we have well-shaped transitions and higher enthalpy values that are also reflect this more packed lipid bilayer. As a next step, as a next step, we tried to encapsulate a bioactive ingredient, and specifically resveratrol, which is an insoluble compound, as an effort to maximize its loading capacity and have a controlled drug release. And as a result, indeed, the utilization of these complex nanostructures, they had as a result to a controlled drug release kinetic, probably due to the highly tortuous porous network of the lipid bilayer architecture. And interestingly, the exact morphology reflected also the drug release kinetic. For example, in the cases where we had a higher grade of channels, like in this figure, we had a higher concentration released and also more faster release compared to the other cubic structure of less channels. Also, we had the higher release concentration when we had lower organization, as in the case of micelles. So the architecture of the polymer stabilizer affects the physicochemical characteristics and the grade of the complexity of the nanostructures, that it is highly reflected also to the drug release kinetic. And now let us go to the final step, which is the final evolution of the nanostructures to highly cationic content, stimuli-responsive, stealth, and subcellular targeting. For this scope, we we combined all the different polymeric stabilizers that we used in the previous steps, along with a quaternized copolymer that has both partially quaternized the localized cations of triphenylphosphine to have strong cationic potential, along with 3 amino groups in order to retain its pH and temperature responsive behavior. Again, there was a great variety of combinations that we tried of different lipids and different combination of stabilizers and different concentration of stabilizers. And all this combination, of course, they reflected a different physicochemical behavior. For sure, all nanosystems had a strong positive zeta potential due to the localized cations. And also a morphological reconformation that was assessed by static light scattering due to the pH-induced transition of the PDMA chains. There were different degrees of colloidal stability upon time according to the used lipid. And all the systems, they had, fortunately, a pH-dependent transition of the charge due to the PDMA. That it is very useful to be utilized further for the nanoparticle internalization, endosomal escape, and targeting a release to organelles. As regards the temperature, there was a temperature-reduced morphological alterations that were non-reversible due to the polymer-induced reconformations. Also, that was a different pattern, non-reversible in GMO lipid and reversible in feed lipid. And the good news is that we finally managed to totally control the interaction with the serum proteins, because in all systems we had stealth properties, different modes of ionic strength depending on the charge. And let us go now to the complexity characterization, wherein again, the formulation parameters of the type of the lipid, the polymer, and the polymer concentration leads to different grades of complexity. For example, here it is the quaternized polymer alone, wherein we have different a morphological variety of ordered and less ordered nanostructures. We have both double diamond type symmetries and primitive symmetries. Here it is the combination also with polymer of polycaprolactone, when we had a pattern of ordered nanoparticles that were covered by intersecting lamellas. And here we may see the interaction of the addition of a gradient copolymer in combination to the localized one, wherein against the gradient copolymer yields to a highly packed organization of the membrane and an increased percentage of the structures exhibiting higher grades of internal organization. And a very interesting figure is the transition of the morphology and of the complexity when we go to altered pH and temperature conditions. We choose to lower the pH and increase the temperature in order to simulate pathological conditions. So we had a clear disruption comparing to the initial state, and an absence of regularly ordered nanostructures and an absence of periodicity. We had these sponge-like nanoparticles that were completely disordered, along with some bulky nanoparticles. So it is reflected also a stimuli-responsive morphology. As regards the fit nanosystems, there was a higher grade of internal organization, more compact nanostructures of cubic type and multilamellar ones. And some specific patterns that were not found in the GMO lipid, that is this type of nested cubic structures in intersecting lamellas. Also here. And as regards the microenvironment, we had the different patterns of micropolarity and microfluidity when we changed the lipid. And as regards the thermal characterization, the MPOX, the gradient copolymer, once again had higher enthalpy values that it is reflected in this, in these figures. These are the figures with the highly grade, with the utilization of gradient copolymer. Our nanosystems were evaluated in vitro in cellular lines when we found an abscess of cytotoxicity, and they were also monitored via confocal microscopy and were found to target lysosomes. This is a very useful property that can be further utilized because lysosomes are organelles that are highly related to many diseases. So the targeting delivery of active agents like resveratrol, which is also related to the lysosome and how can resveratrol induce autophagy and apoptotic cell death in cancer, it would be a very useful property in therapeutics. As regards the drug release kinetic, this physicochemical and morphological pH and temperature responsive property is also reflected to the drug release kinetic. We saw that in all our systems we had a stimuli-triggered controlled release. And probably this is due to this complexity disorganization in altered simulations, in altered conditions that simulate pathological conditions. We may remark that these morphological rearrangements that we found via cryo-TM can act as release promoters. By controlling the formulation parameters, we managed finally to have stealth, stimuli-responsive, and subcellular targeting multifunctional nanosystems. And from the whole study, we may conclude that if we use liquid crystalline nanoparticles as a case study of high grade of internal structural complexity, that complexity is strictly dependent to the formulation, and also said complexity is found to be adaptable to environmental parameters, we may yield to stimuli-triggered drug release kinetics, stealthiness, and all these targeting abilities that eventually yield to multifunctionality. And also, formulation itself was found to be a multifactorial and complex process. So, if we manage to navigate the complexities during drug formulation via rational design and robust techniques, then we may finally have safe and efficient and innovative pharmaceutical products. And at this point, I would like to thank all these people that were working in the study, starting from my supervisor, Professor Konstantinos Demedjos. And I would like to thank you all for your kind attention.
Thank you, Dr. Koudoulesi. That was a really interesting presentation. I think we have time only for one question from the audience. Is there anyone that wants to ask? I think everything was explained, so thank you so much.
Thank you very much.
I think we have a coffee break now, so we can move outside if you want.
Hello, everyone. Welcome to our today's session. I would like to welcome Professor Panagiotis Vlamos, Professor of Computer Science at the Ionian University, who will present his work entitled Bifurcation Diagrams and Stability Areas for Clinical Datasets. Welcome, Professor Vlamos.
Thank you very much. Honored to be invited here by Professor Demedros, Professor Stavridnoudis, and also very glad to be in the same session with one of my precious friends, a great scientist, Dimitris Vlachakis. Today's talk is about bifurcation diagrams and stability areas for clinical datasets. We rarely have the opportunity to speak with this topic to a conference with audience that are dealing exactly the same area. So I'm very pleased to be here. A few words about mathematical modeling. Mathematical modeling is something that we know we're practically dealing with without the name for 2,500 years, yet the methodologies that are used differs all the time, and also this is the case that I will present to you a completely different methodology, which addresses the contemporary era with data. So, if we address to Claude, they say that they recognize that mathematical modeling is the fundamental language of itself, of AI. And also AI recognizes that mathematics is the structural material from which it is made. Yet the main focus here is not the mathematical modeling. And this is very interesting. It's our ability as mathematicians in clinical sciences to have data-driven methodologies. That is, we have to represent the data with a strictly clear computational meaning, easy to be used and explored by high-performance computing methods. We have at first to work with data classification, and before we move to mathematical modeling, to have a set of data that will establish the proof of concept of what we are planning to do. I will show you an example afterwards. So it will be not so theoretical. The data analysis and meta-analysis of data is presented here in order to see that we have to delay that. Bioinformaticians mainly push the methodologies and the high-performance computing tools to be used in the beginning, which is a major mistake. What we can see is that going through the mistakes that we do, methodological mistakes, is that there is an incorrect use of biological representations for computational purposes. We have deep learning, we put deep learning in big data, and we expect that we have results. This is not the case. We have incomplete application of computational tools to structured data sets. We have mathematical assumptions based on models rather than data. This is a huge turn in the methodology of mathematical modeling that is mainly accomplished the last 10 years. And we don't have to use directly high complex computational tools, and we have to rely on computational power resources, and yet see exactly in the clinical data sets that we will deal with the lack of data methodologies for collecting them. There is a necessity yet of compatible data representation for high-performance computing. This is not, it seems like it is something logical that has had to be done, yet it is not the case. We are still using data sets and data collection that are improper for high-performance computing. We do not accept the high complexity of things. There are research groups all over the world that they are seeking for one biomarker for example, for neurodegenerative diseases that we use as a case study, where we're dealing with 1,200 different biomarkers, and yet they seek for the golden biomarker. There is a necessity of open data systems. This mainly has a background that when we have complex diseases that evolve through the time and we really do not know the biological mechanism, we cannot have a mathematical model which is derived from the beginning and it has exactly the set of parameters. That means the crucial variables that on them rely the model from the beginning. We have to have an open data system, and we have to include any time that a new parameter, a new biomarker is involved, that we can put it inside the system. The non-linearity. And this is very interesting about also this conference and the work by Professor Demedjos and Professor Stavridoulis. They have seen the non-linearity in all the models behind the biological systems that they are dealing with years ago. That's very impressive. For us, for the mathematician, it's obvious. Yet, this information, which is a huge difference in what people are doing the last 2 decades, is not obvious to everyone. Finally, we are in the first, it is the first time that there is the biotechnology systems and there is the computational power to deal with time-dependent databases. That means we stop eventually to have pictures of what is going on to a phenomenon, and we have the whole movie, the time-dependent data that are working with that. Is computational power sufficient? It's getting sufficient all the time, and the main thing is that we have lived an evolution that no one expected the last 20 years. In 2005, we did not expect that there will be a computational power of 10 million kernels that can work together as a supercomputer. And what was something that we could not imagine in our field, in informatics, it is that we will have eventually access to them. This was crazy. For example, for our lab, this happened in 2017, that we could access a supercomputer and have our data worked in that. So the change that happened now is that we are not making, as the last 2,500 years, the mathematical modeling, try to understand what is going on and adapt this mathematical model to the world. This was the way that physics, all the physical science and mainly mathematics have worked. This is different. This is now that the data have a power, that why we say data-driven, to give us, in a different way, the verification of models in the general form that we can perform at the beginning. A lot of requirements: model interpretability, reproducibility of results, algorithm transparency, interdisciplinary collaboration, and all that. But the main thing is that this started to work. We have made a research cycle working as a case study in Alzheimer that we have developed 15 years ago. And this was that we're dealing with a circle that we're moving forwards and then back in order to verify all the time the credibility. So we don't start with a mathematical model. The mathematical model, if you see, is the fourth stage of the methodology, but we started off understanding the biological mechanism at the extent that we can know, the development of a biomarker system, and then having the computational tools that can predict separate biomarkers with a deterministic way. After that, we make a mathematical model. I have to admit that the first attempts for a mathematical model give us a credibility around 55 to 60%, which is nothing. It's garbage. Okay? But the main thing is that we deal with that by going back and forward and arriving sometimes at 95%. This is done through approximating the model and go back and including in an open system more biomarkers with exact computational tools about them and verifying again, modifying the model from the beginning. What we have seen is mainly that the bifurcation diagrams, which are a critical notion in what we are doing, is showing in a profound way the stability areas. So if you apply that and see it as the patient's evolution in a disease, this is crucial because you see when it is stable, that is asymptomatic, it has not the disease. And you can see also when it has the disease and when there are transition points, which is very, very critical. One of the problems is that in the minds of biologists, doctors, clinical doctors, the way that a disease has an evolution in time is like X squared. Something is growing, and suddenly something has happened. Yet this is not the case. We started seeing that there are turnovers and difference in stability and also in time by the bifurcation diagram when we started to work in deterministic models for Alzheimer's disease. Our work was promoted through a very significant 7 years up to now collaboration that we have with the Precision Medicine Center of Johns Hopkins. They provided to us with an exclusive collaboration their data, anonymized of course, which were huge and valuable. And also they have provided to us their clinical evaluations in all the findings that we get. And this is extremely good. So we started dealing in Alzheimer's with 750,000 files. We dealt with 930 different patient features for each patient, and we have more than 5,500,000 visits. The direct data analysis was awful, and we started at first to examine what will be the credibility of making a decision support system for predicting dementia within 5 years from all those data. We arrived to the best that we could. This was something between 71% to 77% credibility. And yet this was not enough. You can see the work that has been done. It was training iterations that were crazy. It's more than 1,275 training iterations with all this huge data. This gives us approximately a 75% probability of dementia in a 5-year decision support system for prediction. We did not stop there, but we started using deterministic mathematical modeling according to the notions of this conference. That's why we tried to see if we can first construct the bifurcation diagram, which is completely crazy and opposite to the mathematical methodology, the mathematical modeling methodology, and see if this bifurcation diagram could show us the difference between stability. That means the difference between healthy and people that moved to dementia, transition to dementia. What you can see is that all the high performance computing methods have failed at the beginning. You can see all that. We tried every one of them. The model for the mathematical model for dementia exists, but it's very vague. It has been proposed in its more complete form in 2016 by Friedman, and a great mathematician. Yet, if you use it directly, also fails. This was the model results that when you have the model and you put the data, you end up to a failure. This was the second difference, again failure. So we have started to look to models with the use of around 10,000 different possible solutions. So we had the model that we knew that governs dementia. We have the data, and we had the solutions, possible solutions. These were not aligned. This was crazy. Okay? So we had a huge failure that we knew that the model theoretically exists. We knew the real world data, which is very valuable and also are true. And then we had possible solutions that we can put inside. This did not work also. So you can see that there was a repetition of failures that we have to deal with. The last case that we did, this is also a failure, is that we put the generalized model, but we left the data to try to make the difference. That means, that we have used more than 300,000 possible functions that would give us data separability concerning all the persons that were not having dementia and the persons that are having dementia. So the complete separability was the first stage. After that, so we end up to this. You can see those are the health patients and AD, Alzheimer's disease. The second is that we got through there and had a possible bifurcation diagram according to the separability. And this is the green one. So what we did is that it's completely a data-driven technique, never done before, that we form the data separability from the ones that are not patients and the ones that had Alzheimer's. This is also in time, or the bifurcation diagram. We formed the bifurcation diagrams and then started to acknowledge the exact mathematical model that was represented in this way. And this was the case. We rephrased the problem. We found the mathematical model with the equation. We found the exact bifurcation diagram, and we put it in use, having this result to the 750,000 patients. The interesting thing is that it works to the new ones also. So it is verifiable every day with the new patients that enter the system. What does this give us? This gives us, afterwards, we put A-based optimization in this stage. So you understand now that people in our field are using AI and bioinformatics in the first step, which is a complete failure. Okay. Then in this stage, we started getting trajectories. That means we have the possible prediction, not only that someone will have dementia or not, but the exact trajectory in time according to the values of biomarkers that can be used, and this can be prolonged not to 5 years, but to 12 to 15 years. This is what we are working. So what can you see is when you are in the green area, when you are near the bifurcation diagram line, you are completely stable. We say it in mathematics asymptotically, not asymptotic, asymptotically stable. When you are in the green area, you are stable. And when you are in the borderlines, you are in danger, in risk of having transition. Also, this bifurcation diagram explains why people collapse. If you see, this is a diagram after 12 years that someone inside the green area is still stable, doesn't have Alzheimer, and suddenly it goes and have Alzheimer after 12 years, while their biomarkers ID is growing faster, while others are going to the areas like the two at the edges very, very soon. The other thing that this model gave us is exactly transition points. So we have the points that something should happen. Something will be, for example, pharmaceutical intervention or something else. But you know exactly when to do it. You want to do it earlier or later. Earlier could be catastrophic. Later has no meaning. Sorry, and the other thing which was is very interesting, and now our clinical partners are working on it, is the 8 clusters. If you can see that you have transitions, but also you have 8 clusters, different, the ones with different colors that people are getting in the dementia area, and you have to find the connection between the same phenotypes but different biomarker sets that leads you there. So the clustering exists. The mathematical way of proving it is already done, but yet you have the clinical findings to be interpreted again with human in the loop. You cannot do it by yourself. AI cannot do such things. Then we have a pure roadmap for data to knowledge translation. This is an example that I have shown you. So we have application of data cleaning, pre-processing techniques, feature extraction, of course, feature extraction with an open data system at the end of the day, selection of computational data representation, data-driven AI methods for identifying stable and unstable regions, application of mathematical mapping models, classification and clustering, clinical interpretation of the results, and then blind testing using existing databases, and investigation of transition with characteristic features that lead to that. What we really understood after that is that the most valuable thing is the alignment. For the first time, you have an alignment of data, annotation, and with disease. The second is the bifurcation diagrams that explore in such a way stability, instability. Third is trajectories that lead to exact time points, time-dependent points that decline. We have a transition points of phases towards the disease. A mathematical model that can work with time dependence in deterministic way and goes back and forth in time, and the new way that the clinical data should be treated in different clusters. All these were for the first time aligned. Thank you very much. I think I made the time.
Thank you, Professor Vlamos, for your presentation. Are there any questions from the audience?
Thank you very much for the presentation. Very interesting results. It's very important for certain disease to identify and use data from other patient prognosis. I was going to ask you if by chance, if not by chance, that for those patients that you can predict in a short time, like 2 or 3 years, or 5 years, suffering dementia, did the hospital provide any medication or to extend the well-being?
No. Yes. What we are currently doing is have a variety of profiling. So persons think that Alzheimer, for example, is one disease. The clinical doctors that are doing research at our time are talking for 8. We are thinking that it's hundreds. So the next steps are we're trying to build a model that will be included at the Precision Medicine Center of Johns Hopkins for the newcomers, and providing the possible trajectories according to their initial biomarkers. So after some visits, you're starting to have a clear view of the matching. So the matching has possible, in profiles, has possible, the different possible treatments or perhaps drugs. The drugs are you should understand that all that we are dealing with, it's evolution of last months. So we know what to do, but we're thinking we are in the correct roadmap.
Thank you very much, Professor Vlamos. And now I would like to welcome Professor Denis Douroumis from the University of Nicosia in Athens to present his work entitled 3D Printing of Personalized Medications, Point of Care and Scale-Up Considerations.
Thank you.
All right. Good morning, everyone. Thank you very much for the invitation. So the topic is slightly different from what we have seen so far. I'm going to discuss about 3D printing of personalized medications and spend some time to discuss about scale up and how we do it at the point of care. So a few things about 3D printing. The very first 3D printer was developed in 1984, and that was done from Chuck Hall for 3D corporation systems. And back on the day, those 3D printers were very bulky, very expensive, and with a very low resolution. So over the last 10 years, we've seen a tremendous progress on the development of 3D printers, which are cost-effective, very fast, and also provide high resolution. And we've seen that we have several applications, not only for healthcare, but also different sectors like automotive, design, art, and even for toys. It was back in 2015 that we saw the first product in the market from a company called Aprecia, and they put an anti-seizure medication called Spritam. It was a levetiracetam, and they use a powder bed technology. So this technology is for mass manufacturing of 3D printing dosage forms, and we'll see later on that there's a kind of discrimination for these technologies. But the whole concept was to develop a porous tablet where once we place it on the mouth, it will dissolve in a few seconds. And we see on the middle image how these tablets look like. So I'm sure a lot of you have heard about 3D printing, but what actually 3D printing is a technology where we use it to construct 3D objects, relying on the layer-by-layer deposition of different materials. There's a wide range of materials on a computer-controlled built platform. And usually, there's a wide range of technologies, as we'll see later on, but the most common technologies are those you can see on the schematic diagrams. We have the fused deposition modeling, where we have a flexible filament that usually is loaded with a drug substance or just polymers for those that use it for prototyping. In the middle one, we have what we call selective laser sintering. And in this case, you can print objects by using only powder blends. You don't have to have a filament because it has several restrictions. And the last one is called stereolithography, or there are similar techniques like stereolithography. And in this one, we use a resin which is photopolymerized. And the selection of the technology we'll see later on, it depends on our needs and the specifications of the project. So for the last 10 years, there was a tremendous interest, not only from academia, but also from industry for the development of 3D print technologies or products that have found several applications for healthcare. And there are several reasons that why we want to use it for healthcare applications is that because of the high diversity on different 3D print technologies, we can identify the suitable one that meets with our needs. What is very important when it comes to healthcare applications is that we can use printers for personalized dosage forms that meet the patient clinical needs. We'll see later on some examples. Of course, they can be used for point-of-care applications, which means we can do 3D printing in the hospital or even in the pharmacy. And we can also design what we call polypills, which means in a single tablet, we can have a number of more than one drug substances. And in this way, we could potentially address the polypharmacy for elderly people. And of course, because those printers have high resolution, we can use them to print complex geometries. We'll see several examples later on. So there's a lot of discussion over the years about personalized medicines and how this could help patients, the well-being of the patients. And there's a strong demand again to develop personalized medicine because we usually describe them as a medicine that are tailored to the individual needs of the patient, which simply means that we can adjust the dose for each patient, irrespectively of the age, of the gender, and we can administrate drug substances, which meet their own, which relate to the patient mass and metabolism. And if we go a step back, we can design the optimal therapy of each patient by taking into account genetic characteristics. This is, of course, something that has not been fully developed, but by taking these genetic characteristics and personalized clinical outcomes. In this way, by combining the medical history of a given patient and also taking into account the clinical data from, as we saw before, from different examinations, we can develop a targeted treatment. And this is very important because we know that the patients vary of different ages. They need different doses and different type of administration. So we are moving to the next step, where at this time we talk about manufacturing of 3D printed dosage forms at the point of care. I mentioned in the very beginning that Aprecia developed a mass production 3D printing technology where they can print thousands of tablets per hour. However, in recent years, there's a lot of demand and discussion in Europe or even US about printing at the point of care, printing in the hospital or in a pharmacy. Of course, there are a lot of road ahead, but the first steps have been taken. So the manufacturing of medicines is because, again, we can address the needs of each patient by working closely with the doctors and the clinicians. The benefits of using point-of-care applications is that we can decrease the cost in the healthcare system and, of course, the side effects and hospitalization time. So if we offer a better treatment, the hospitalization time is reduced, but also can avoid side effects because by adjusting the dose, we walk away from this for the existing approach where one size fits all, which means for all patients, we give the same active dose, which we can find in the market. Of course, we can reduce costs, which are associated with packaging, prescribing, and dispensing, because those dosage forms are manufactured in the hospital, and we don't. There are easy ways to storage them, and what is very important is that it will be administered in a very short time. So that means that we don't have to. We remove demands for or the regulatory demands for long-term stability studies, because those usually are designed for a maximum of 1 month stability. So we move now from the manufacturing, which manufacturer-centric logic, to a consumer-centric manufacturing logic, and what we call we move to what we call digitalized supply chain. Of course, we have a new business model which it's demand-driven, and it requires low investment for the hospital, but offers flexible supply chain with a very quick response time. In simple words, that means that we can produce medications in the hospital where the demand of medication of dosage forms per day or per patient is very less compared to the mass production. So I will move now. It was just for your to inform you what are the current trends in the market, or at least in the industry and academia. So I'll present now a few techniques that can be used for point-of-care applications. So one of them that we have used in collaboration with pharma companies is called micro-extrusion. So we can see on the schematic diagram that this technology is very simple. We have a cartridge filled with a given formulation and our API, and every time we can remove this cartridge and replace it with another API or another formulation or the same one. So the benefit of this approach is that we, by using micro-extrusion, usually those printers are designed to offer excellent printability for a wide range of thermoplastic materials. That means that we can adjust the formulation depending on our needs by using pH-dependent polymers for sustained release or even for immediate release. These technologies are usually of low cost, and they have a very small footprint. So you can put them in the pharmacy, in a hospital. They are easy to operate and very easy to clean. So those that have experience on GMP cleaning in a manufacturing suit, you know that cleaning can take more than a day or even a day. But here the cleaning is much faster and very simple. So you can just replace your cartridge. We can see on the diagram with a new one with a different drug substance. As we'll see later on, the printing quality is excellent and the reproducibility is very high, but also we have very fast printing times, which is very important for small scale up of different batches. And also, as we can see, that these are usually it's a single step process where we, as I mentioned, we don't have to do the blending or develop the formulation in the hospital or in the pharmacy, but we can have those pre-filled cartridges, just place them in the printer, and then we start printing. As we'll see later on, by using this technology, we gain also some other advantages, such as taste masking of bitter APIs. This is very important for pediatric formulations and dosage forms. So, as we can see here, we have, these are some photos and SEM images of dosage forms that have been printed by using micro-extrusion. Now, the actual printing can be controlled by applying pneumatic pressure or mechanical pressure on the system, but also by controlling the applied temperature. Usually, we need a range of different temperatures to print. And what you can see here on these images is that we can control the design by controlling the shape. So in that one, we have very normal tablet designs, but what we change here is what we call the infill density. So you can see these small holes in the tablet body, which we actually use them to control the dissolution profile and also the size of the tablet. Now, it's very important, and we'll see some examples later on, that there are different ways to control the dissolution rate of a given API. One way is, of course, the formulation by selecting the right polymer or design what we call printable inks in an efficient manner. But we can also adjust the dissolution or reduce or enhance the rates by playing with infill density. So you can see some of them, they have a higher infill density and other of them have less. We can even make solid tablets with where the infill density is 100%. So as you can see on the SM images, we have an accurate and consistent layer deposition. This is very important for the reproducibility of the layer print, which eventually results in the reproducibility of the final tablet. So this is an example where we develop 3D printed chewable tablets of ibuprofen. This is very important for patients, like especially pediatric patients. And the idea was to meet the pharmacopoeia specifications in terms of dissolution rates, but incorporate and try to make tablets as small as we can. So in this case, we managed to have a loading of 40% of ibuprofen. Now, what we can see here, this is very interesting because it comes back to what I mentioned before. You see dissolution profiles of ibuprofen with different kind of rates. And this has to do with the actual design of the tablet, but also the selection of the right formulation. So by playing with the different polymers, some of them were pH dependent, some of them were neutral, we managed to achieve different release profiles. Of course, there's only one that will meet pharmacopoeia specifications, but you can see that by selecting the right formulation, the right polymer, and then playing with the dissolution media, we can achieve different dissolution rates. So we further try to improve those formulations, and we wanted to make more complex designs. So we don't want to make any more these round shape tablets, but we try to make it more attractive for pediatric populations, especially for children. So we developed we made those printable dosage forms. They look like Haribo. I'm sure that all of you know Haribo. We also try to make it look like those Haribo and try to mimic the taste. So for that reason, we included sweeteners and flavors. So when children taste these dosage forms, they think this is quite actually it's a Haribo dosage form, and we increase the patient compliance. So these are tables. I'm not going to go in detail, but we use panelists to evaluate the sweetness of those tablets and also the orange aroma. We use the different flavors, orange and strawberry. It depends on the taste or the needs of the patients. So again, by playing with the formulation, by improving the printable ink, which I already mentioned, this is very important. We managed to achieve very fast dissolution rates of ibuprofen. So you can see in most of these dissolution graphs, we have 100% release of ibuprofen between 5 and 10 minutes. And also we, of course, we optimize the taste perception of the API because it's quite bitter. The bulk ibuprofen is quite bitter. And this technology can be used for a wide range of APIs, irrespectively if those are bitter or not. The selection of the right formulation, we can eliminate bitterness by enhancing the interactions of the API with a given polymer. So this technology is now a proprietary technology of Bristol Myers Squibb. We worked with them for 3 years and is designed to develop 3D printed dosage forms at the point of care. So as I mentioned, micro extrusion is a printer like that is a benchtop printer, very small one, and you can use it for printing at the hospital. Now, I'll give you another example where this time we didn't print chewable tablets, but we use the similar technology to print semi-solid dosage forms. So those are in the form of a gel. So the project was funded by Innovate UK, and this is a proprietary technology of Aristotle University in Thessaloniki, Delta Pharmaceutics, and Cubitech Extrusion. The technology belongs to my good friend, Professor Dimitris Fatouros. So we initiated clinical trials in St. Peter's Hospital. Initially, we started working on pediatric dosage forms, but unfortunately for us, MHRA has have very strict regulations, so we are going eventually to administrate placebo formulations. And for elderly patients, the actual clinical trial is going to take place for patients suffering from stroke. So we developed those semi-solid fast melting tablets. We call them fast melting because once you place them on the tongue, they will dissolve in less than 30 seconds. And one of the very important things is not only to develop the actual formulation, which will hydrate very rapidly, but also to improve the printing process. This particular hospital, they have, on a daily basis, they have around 200 patients. So we need to have a very fast print time to meet the needs of all those people. So the printing time was roughly 30 seconds by using a bioprinter. So in 30 seconds, we can have 3 tablets at the same time because those printers, they bear 3 different print heads. And eventually, the concept of this technology is to try to mimic what we call the espresso machines. So we have the dose ready for a given patient. We can print it out and we can cover the needs for 1 day or even a week. And the technology actually works really well. So what you can see here is that you can see those very fancy images. Those were printed by using the same technology. These are semi-solid formulations. And you can see that, especially for pediatric use, they are ideal to attract their interest. So, which means increasing the adherence to the medication. What is very important here to see is that the optimized inks, again, it goes back to the formulation, they present a pseudo-elastic flow, which eventually it enables us to do the printing at room temperature. Those formulations can be very sensitive under heat, so we wanted to be able to print at ambient temperature without applying any heat in the cartridge or in the nozzle. Another very important is the dose accuracy, because when we talk about children, we have to make sure, but also other patients, we have to make sure that we meet the actual dose restrictions. So what we did here, what you can see, is that the dose accuracy scale is linearly related to the print height, which means as long as we increase the print height and subsequently the weight of the tablet, the amount of drug is proportional. So what you can see on these curves, on the top curves, you can see that for 4 different drug substances, the increase of the height is linearly related with very high accuracy to the active dose. This is very critical. So the next question is that, okay, you managed to match the active dose, you do your dissolution profile, which probably meets the pharmacopoeia specifications. So the next question is, does it really work for patients? So I'll give you an example of a clinical study that was done by colleagues in Erasmus University in Netherlands. The regulatory authorities there are more flexible, so they allow them to develop pediatric dosage forms for personalized use. So, of course, by applying GMP conditions and quality control standards, they print semi-solid, again, similar to what we did before, semi-solid fast-melting sildenafil pills, and they compare them with the existing dosage form, which is already in the market. And I'm not going to go in detail, but they use a crossover design for the participants, and one group was given the 3D printing tablets, the other one the marketed product. What they found eventually, with the end of these bioequivalent studies, they found that 90% confidence intervals in terms of the area under curve and the Cmax were within the acceptable limits. So what they have done here is that they prove that a 3D printed dosage form that at the point of care can match the clinical efficacy of the commercial product. Now, what is missing here is that they compare those results with the marketed product. And we mentioned before that the 3D printing technologies are designed to meet the needs and the dose of different people. So this has not been done yet, and this is something that is missing in literature or in the in pharmaceutical industry, to convince people that we can do that for a lot of different kind of patients. However, there was a real proof that 3D printing dosage forms have the same clinical effect with the marketed ones. So now moving to the last part of the presentation, a few words about the scale-up of 3D printing dosage forms. We need to develop GMP facilities. This is a requirement from all regulatory authorities, where we have automated lines where we can print dosage forms with optimized parameters. It's very important to maintain the reproducibility and batch-to-batch consistency, and for that reason, by following regulatory guidelines, we have to apply very strict quality control and analytical tests. And for typical tablets like those I mentioned before, we talk about the mechanical strength, like hardness, dissolution, quantity uniformity, and disintegration profiles. If we make any gummies, there are additional tests that we have to take into account, especially if those administered to children. So we have to evaluate the chewiness, the springiness, and the gumminess of those formulations. A very common approach to address the scale-up at the point of care is to use standardized technology. So that means that in simple words, we have to identify which technology meets our needs and combine that with validated printer hardware. Now, this is a very critical issue because there are a lot of printers in the market, but only a few of them, they have a validated software. Unfortunately, this is something that the regulatory authorities require. We have to also comply with qualified pharmaceutical feedstock and the automated process. The feedstock has to be qualified, and that's why I proposed before that we have these pre-filled cartridges. So we avoid any mistakes or issues if we try to make those at the hospital. And for point-of-care manufacturing, this is the key message. It's the scale-up usually relies on what we call scale-out model. So instead of trying to increase the printed amounts of those dosage forms by using larger printers or faster printers, we can use the same printer in parallel, which is a very common approach in industry. So we have like 2 or 3 of them to print and meet the needs of at the point of care. And of course, that one means that for each of those individual printers, we have to monitor very specific parameters in order to have a consistent production of the dosage forms. That means that we have to control and control the printing temperature, the extrusion rate. This is the rate where the material comes out from the nozzle, the layer deposition, and the dimensions of the products in real time. I'm not going to go in more detail, but for this reason, there are different ways to control all these processes. A very common approach is to use what we call real-time monitoring, PAT tools. So, for example, we can use FTIR and NIR Raman or Raman sensors. What I forgot to mention is that it's very important to not only to have a standardized method and a platform within the hospital or in our pharmacy, but also we need people that are highly trained. The only problem that we encountered, at least in the UK, was that the clinicians or the pharmacists didn't want to get trained on 3D printing. They saw that as a black box. Anyway, and eventually, because we live now in the AI era, it's very important to combine AI and digital twins with a quality by design approach. This is mainly for people in industry, but those can help us to optimize the printability of the dosage forms at the point of care and avoid mistakes that can be fatal for patients. So the last, that one, this is the last slides I want to present to you. This is a slide that generated by Merck. Merck is a leading company in 3D printing, among other technologies. And on the top image, you can see the different steps of the existing manufacturing process for tablets or ordinary dosage forms. So you can see there are different steps, at least 5 different steps. The vision of Merck is to reduce this number of steps where you have only the blending of your powders, and then you can straight print out the dosage forms of your drug product. And the last video clip where you can see how we can print at the point of care. This is a hydrogel that we printed for the delivery of proteins or delivery of proteins. So you can see that how the printer works and the accuracy of the printing. The whole tablet takes about 2 minutes. The aim for this one was not to reduce the print time, but to develop a tablet with a given substance. So, in conclusion, there's a wide range of 3D printing technologies that can be used for manufacturing medicine at the point of care. It's up to us to identify which of these technologies it meets our needs. And it offers several advantages. I'm not going to go again over those advantages. I mentioned them already. It is ideal for, these technologies are ideal for personalized treatment to meet the needs of individual patients, from young children or up to elderly people, reduce the treatment cost and in the healthcare system, and introduce a new business model, especially for pharma companies. So thank you very much for your time.
Thank you, Professor Deroumis, for your presentation. Are there any questions from the audience? No? I have one question. What is the biggest challenge in transforming 3D printing from laboratory technology into a manufacturing technology?
To me, from my experience, there are 2 issues. The first, it relates to the regulatory authorities, because they're very strict and they have, again, from my opinion, they have to be very flexible, or at least try to be flexible. I'm not saying not to follow guidelines, regulatory guidelines, but these are new technologies, and the MHRA, for example, they believe that we have to follow exactly the same regulations to the conventional manufacturing. We've seen a lot of initiative from FDA, but still we are a bit way ahead. And the second important aspect, because the 3D print technologies are already there. We can use them, we can adopt them, we can design and validate them for point-of-care manufacturing. There's no doubt about it. The second reason is the pharmaceutical companies, and this has to do with their profit. Big pharmas, they have a margin or threshold for their profit. So if they realize that they don't meet these expectations, they're not going to move to 3D printing. So, for example, we have this paradox that companies like the Aprecia or Merck, now they work on for the mass production of 3D printed dosage forms. Instead of working downscale them and work for point-of-care applications, they work again for mass production. So they use this layer-by-layer deposition method, jet binding, because they see that in that way they are not going to reduce their profit. So regulatory authorities and pharma companies, which means in the future, what I foresee is that small companies or companies, they have a margin of profit, let's say 100 million per year, they would move to point-of-care applications. And that will focus on rare diseases, for example, not to very common diseases.
Perfect. Thank you very much, Professor Denis. And now I would like to welcome our third speaker, Professor Dimitrios Vlachakis from the National Encyclopedia University of Athens, to present his work entitled Nonlinear Biology, From Stress to House and From House to Therapy.
All right. Thank you very much. Super happy to be here. I would like to thank Professor Demetrios for two things. First of all, for inviting me and getting me here. And secondly, for putting me in the same session with my very dear good friend, Takis. So today, we're going to talk a little bit about how we can include stress as an entity to fill in the gaps where biology and medicine and informatics somehow blend together, but also fail to see the big picture. So we are here to talk about chaos. And what better place to start rather than inside my head. And of course, because we are all very good scientists, there is only one thing that you can see, you can find inside my head, and that is the Nobel Prize. And since we want to talk about the Nobel Prize, actually I want to talk about the Nobel Prize, I'm going to take you through a project, a consortium that we are a part of. It's the Adam and Eve Consortium. I don't know if any of you is familiar with this consortium. And we participate representing Greece. And it has to do with the so-called Nobel Turing Challenge, where a lot of countries got together and we decided that, let me see if I can get the pointer to work. Okay. So that thing, the Nobel Turing Challenge, is a project where we try to establish a high autonomous AI system that can perform top-level research. That can perform top-level science, and that level, the discovery will be so brilliant that it will honestly deserve the Nobel Prize. But it has to be done through data and AI. How this thing operates is it's based in a game of Go. So we have we monitored all the options, all the alternatives that you have when you play a game of Go, and there is approximately 10 to the power of 170 different moves, options that you have when you play that game. And we know that the red circle here is a game of Go that has been recorded in the past. The pink one is enhanced options moves using an algorithm, and the green one is all the options that you can have on a specific board where you play the game. That is that's not very different from scientific discoveries. Here again, the red spot is the knowledge that we know, the amount of information that we have right now, and then we have the pink circle, where is the human discoverable knowledge, what our brains can think of. And then we have the knowledge that can be discoverable by using a hybrid AI informatics approach alongside the human mind. And then, of course, there is the AI-driven exploration, which is a vague area outside that hybrid state. So there is a very good Greek community, actually, that has helped us a lot, and I would like to mention those people. So these are 2 Nobel Prizes. This is a Nobel Prize in Medicine, 2012, and the Nobel Prize in Chemistry, 2000. And those people, those guys, they both got the Nobel Prize, but using a completely different approach. So first of all, we have the Yamanaka factors. And this guy, he said, he will reprogram a cell to gain stemness. He did a search. He looked for 24 genes. Then the 24 genes somehow worked. He did a leave one out experiment, and he got a Nobel Prize. So he had a hypothesis that actually worked, and he got the prize for that. And then we have the Alan Heger Nobel Prize, where this guy was looking for a thin film formation, and then by accident, he got something else. He optimized that accident, and he got the Nobel Prize for the accident. And this has happened a lot of times in science. So how that is a deterministic, let's say, approach. You have a vision, you make it work, okay, but how can you predict that? How can you program that? So the temporal order of discoveries doesn't have to be linear. If we have here the significance of discovery, maybe things don't go very, very well, and then suddenly something happens, and that something makes a huge difference. In science, we used to base our approaches on hypotheses and try to use specific data sets. So we have one data set, we make a hypothesis, and then that leads us to verify something. We get to another hypothesis from another set. So this is a very deterministic, and we try to break it into manageable pieces. And sometimes that is not it doesn't apply very well to non-linear problems, because this is the reality between the human cognitive representation of one human and another human. We all know our stuff, but we may agree on some stuff, we may not agree on some other stuff, but there is a part that overlaps that we all agree. And if we use an AI assistant to automate first and then to become autonomous, maybe something wonderful will happen. So the system works like that. You have a community of scientists, and then you augment that by an AI scientist, and then you have the stakeholders, and then you just look for agents in the data that you have in order to make synthetic instances that don't exist. And instances that don't exist means exactly this. Conceptual knowledge is backed up by mathematics and system-oriented theories. So in biology, if you make a discovery that disagrees with what we know about DNA, RNA, and proteins, you throw it in the bin, because fundamental laws and theories have to be met, okay? So what we know right now is that this is the part of biology, the blue blob here is the part of biology that we know, but this possible biology is biology that is in full agreement with all the theories that right now stand in biology, but hasn't been discovered yet. So if we train an AI system and we get it to learn exactly the fundamental laws of physics, chemistry, and biology, and now that is a library that that system has always to refer to, okay? and then it goes through the literature and discovers all the knowledge that has been generated based on the fundamental principles, that will be the blue part. But then, that gray part is possible biology that is in full agreement with fundamental laws, like gravity, like chemistry, like all the reactions, but it's not published yet. So we want that information, because that information, since it doesn't disagree with fundamental laws, could mean something biologically significant that we haven't thought of right now. So we know that nature is not linear. Of course, life is not linear, and disease is not linear. And we have become accustomed in studying biology as if every cause has a single effect, which we know now that it's not the case, because organisms behave as adaptive systems. And this is the whole story behind the Nobel Turing Challenge, where we have the human scientists who do all this boring stuff. We read a lot, we do a lot of hypotheses. Actually, I'm very good in making hypotheses. I'm very bored to analyze and build theories, but then we have limited time and limited minds. And then we have the AI scientists who can do all of those stuff based on mathematical models that are pretty reliable if you know how to handle them and you don't just throw a lot of information hoping for something wonderful to come out. So we have an iterative step where out of mining, we do the hypothesis and then the analysis and we deploy the model. Right now, that thing has been applied. It's operating for about a year, this consortium. And Adam, one agent, there are two agents, Adam and Eve. Adam has already discovered a repurposing, no, he didn't discover, he designed orphan enzymes in budding yeast, and Eve managed to perform a repurposing of a drug for a DHFR, as a DHFR inhibitor, which is now in clinical trials. So somehow it has already shown some hopeful and fruitful applications that may come in. And this is where we come, because we want to put stress into the equation. And stress, in our mind, is something between all the computational stuff that we can do and adaptation. Adaptation in biology, but also on how you design the model, the mathematical model that you're going to deploy into your algorithm. So we have a lot of information that comes from many different walks of life in biology. So we know that we have all those networks of genes and proteins and metabolites, that hormones that work together. And then we have stress, and we have the butterfly effect and all the attractors. And we are mainly focused right now in this thing, aging as loss of complexity. There is a hypothesis that we are trying to build, that as long as you maintain your complexity, you remain young. If you start to lose parts of your complexity, that could be a decline in complexity, and that decline in complexity could be senescence, could be cellular aging, not chronological aging. And we know that because now we have all the different omics that we can simultaneously analyze, and we can have vectors between all the different omics layers, where we have all the genetics and metabolomics and proteomics and the microbiome. And we know the healthy state are those lines connecting the dots. And then we have a pre-disease state and the disease state. So if you calibrate those different multi-layers, if you train them in very well-defined, clinically characterized groups of healthy people, so as Professor Vlamo said before about the work that he has been doing in neurodegenerative diseases, if you here have young people that they don't have any sign of dementia, and here you have all the Alzheimer's patients in your cohort, here could be the MCI, the in-between stage. So if you understand how those dots and lines change the topology from that state to that state to that state, then you can design a hypothesis, a scenario on how you can tackle that. So we try to find a balance, the continuum of what we call allostatic response. We have homeostasis and we have allostasis. Homeostasis is stability through constancy. We try to remain stable. Allostasis is achieving stability through change, because nothing is stable in this universe. For many, many years, we have been, my professors, my teacher, I have been teaching a lot of things about homeostasis. The truth is that homeostasis doesn't exist. Every second, every minute, we are 1 second or 1 minute older, and we have a different composition in our biology, in our body. So we could consider homeostasis as a tool to understand a biological phenomenon in the same way that we think that the area outside this building is flat, although we all know that the globe, Earth, is a sphere. But for very small portions of the globe, you can consider it flat. So when you buy a piece of land, you just measure 2 dimensions, you give the money, and you're good. Although you know that you are buying a little bit of the curvature of the Earth, okay? So this is exactly what we try to produce here. So maybe that oscillation has a lot to say on the adaptive allostasis. And we know that because stability becomes chaos in many, many scenarios where we try to reduce the complexity of the human biology in histograms and mathematics and put them on a computer and try to understand the biological phenomenon. Because maybe you have the genome, epigenome, whatever, but those lines, they go across the layers. And then when you try to deduce something, when you try to find what happened to my hormones here, and you look at the outcome may be not on that line, maybe on that line, because that hormone has epigenetically altered an enhancer on some gene, and that gene now is overproduced, and there is a lot of RNA, and that RNA is the answer to what happened on the metabolite, on the hormone level. So we need to understand how these things work. And of course, now we have the microbiome as well, because we know that a lot of hormones and a lot of small molecules, metabolites, come from microbes that live in our body. And we think that we could bring all the very, very early knowledge that we had about evolution from Lamarck into play and see how that could be applied in the molecular world. Because evolution, and there was this guy, Dobzhansky, Theodosius, who said that if you want to, nothing in biology makes sense unless you see it under the prism of evolution, okay? Because evolution has a very, very strong statistical significance because it's observed throughout time, and something that nature maintains for a lot of time. There is a thermodynamic law behind it. Physics want it. And if you take that for granted and you use it as a control, you have a much bigger chance of getting something significant rather than just comparing a few experiments that you did in the lab. So what we think we could do here is we could move between attractors. So we could have a health attractor, then the inflammatory attractor, and then the degeneration attractor. So you move from one place to another, and all those things are like when we do molecular simulations where we have a local minimum, a global minimum. Of course, there is no global minimum in life. At the end of the day, everybody is going to leave this Earth, move to another place. I hope it's more bright and more beautiful. But until then, we could think that health is here, and then inflammation is in between the degeneration attractor. So there are different ways. You have to achieve inflammation, but you go from a healthy state to an inflammatory state, and then you come back to that healthy state, and then you go back again, and then you come back, and only then you can move to the degeneration state. So it's not a linear thing that you go from a healthy state to inflammation and then to degeneration. You have to walk back and forth into the inflammatory attractor. And when you do that, maybe because that ball is heavy and the ground is very soft, it shapes the ground, as Lamarck said back then, and when it creates roots and waves through the different states, and only then it can move to the next state. And we have done some work on that, on a couple of papers that we published about a couple of proteins. One of them is the STING, the stimulator of interferon genes, a protein that we know started in bacteria many, many years ago as a defense mechanism against bacteriophages, viruses. And now we use that as the protein that triggers the immune system and the interferon response in our body. And then we have this protein, the DNA PK, which is a DNA protein kinase. We know that protein phosphorylates. We know a lot of things about that protein. There is a crystal structure of that protein. But recently, we published a paper in Cell where we discovered that this protein has also a catalytic site that cleaves cyclic dinucleotides. And cyclic dinucleotides are the triggers, are the modulators of STING. So that protein is not just doing the epigenetic stuff that it's doing, it's also modulating if STING will start or not. And we did some knockout models, and we discovered that you can go about this place, and then you have all the different perturbations here if you're gonna go from the inflammatory attractor to the disease attractor. And this is what we ended up, the theory that we are trying to prove. So you have a healthy attractor, you have an instance where you are healthy, and then you have the degenerative attractor, you have the pathological attractor, and you have an adaptive attractor. You can go from one place to another, but you see, when you leave that place, you never come back. You don't have enough energy to climb that wall back again. So now we use this as 1, the value of 1, and you can never reach 1 again, as it happens in many, many cases in physics, maybe due to friction or something like that, okay? Or resistance or time. So now the choices are you use that dynamic energy, you go down the hill, and you can end up here, here, or maybe you have enough strength and momentum to go to another attractor. And that other attractor, it means that you went through a disease state and you're healthy again. So we should stop trying to analyze all the data that we have by using the same healthy control in the experiment, because after you have been through some pathological states, you can no longer compare to the same healthy attractor. And we now have a before therapy and after therapy attenuation, where you can find yourself in another healthy state, not a pathological state, but that's a different state. So stress is something that has been neglected for many, many years. There is a lot of work on stress, of course, and many, many publications. A lot of people have made their career on stress, but in my mind, stress is a little bit different than the biological and medical dimension of stress. I like to think of stress as magnetism, as gravity, as a wave. And I think that stress is the driving force of evolution. And we know, we have information about that. So if you look in low stress environments, where you have stability and conservation, you can find all those species because, some lizards in some isolated islands, there are no predators, there are no pathogens, so they are not scared. Nobody's gonna eat that lizard because there is no predator in that island. And that is a low stress environment. And because there is no stress, there is no DNA damage, there is no push and genetic drift, so DNA remains the same. And now we know that we have sharks, which are apex predators. A shark is not afraid that it's going to be eaten by another animal, fish in the sea. So their DNA has been unchanged for 400 million years because there is no predator and there are pathogens. So why change? If there is no stress, DNA doesn't change. But if you go into stress scenarios where you have bacteria and you have a lot of antibiotics, viruses, you have the immune system and the drugs that we administer, humans, where we go through all the different levels of stress, from psychological, social stress to medical and biological stress, there we have a huge genetic drift and things change. And we know that we can go from stress to chaos and from chaos to therapy if we take those parts into account when we design the models. So we have the stressors, external stressors and internal stressors. We go through the turbulence where you change from an attenuator that you are healthy to a disease and you come back to health, but you come back to a different state of health. And then you can do that therapeutic windows where you take the molecular engine and you have a crossroad that you can monitor, you can see how that thing develops and which route is going to choose. And sometimes we hope that maybe we can influence which way it can go so we can reach a new healthy state faster. We know that Turing challenge is based on mathematics, of course. So you have order, and then something goes bad. But then, through complexity, you try to reinstate a new order. And if we can see how we can go from that order into complexity, then we can start predicting some answers and understanding life. As Socrates said, the secret of change, and I like that not because it's a good closing thing, because he also talks about change. And in my mind, change has a genetic drift and shift and evolution inside, is to focus all your energy, which is also true. There is no change if you don't have metabolism and mitochondria doing all the work. So I think this is a brilliant thing that he said. I don't know if it was, but it fits so nicely into genetics and biology. So don't fight the old, but build new, something new. Thank you very much for the attention, and I'm happy to take any.
Thank you, Professor Vlahakis, for the interesting presentation. Are there any questions from the audience? So
if there are no questions, you either understood everything or nothing. So,
do you think that AI, the application of AI nowadays, is a stretch for a human, or it's the opposite? Like it helps improve human or down?
AI is a tool. And as Professor Vlamo said, if you just hope, put your money on AI, you lost everything. AI is a machine, is, as I said, the tool, like a scalpel is to a surgeon. Okay, if you give the knife to me to make an operation, it will not go very well. Okay, but in the hands of the expert, someone who knows what he's doing, I think miracles can happen. I think AI is not putting any stress or taking away any stress. It's how we use AI that could bring stress to our life, because if we don't use it properly and we hope that we will publish soon something that we don't even understand, then yes, that will bring more stress in our life. because now we will have failed in one more thing, AI, and failing again and again with things that you don't understand is stressful. So I think we learn our stuff, we know how to use it, we choose the properly annotated data, and wonderful things will happen.
Another question.
Please.
I kind of disagree with your comment, because I think AI is not just a tool. It's like an android or a robot. We train to do things. At some point, we will do it better than us.
You mean better than me? I don't think so. That will not happen.
For example, we academics, we train the AI and it's better than us. We, of course, we provide the right data and train it for a long time, can come up with better teaching approaches or teach much better.
Yeah, it's true. But then again, you need to know someone built that machine, so someone knows what he wanted that machine to do. So in that perspective, it cannot outperform its creator yet. I don't know. In the future, I don't know. I hope I will not be around that day.
And Professor Demetrios?
Excellent presentation. I have a question. Is there any relationship between entropy and attractors A and B?
Yes, of course. And there is a bigger relationship between enthalpy and attractors, because what we try to see is we move from an equilibrated system to another equilibrated system. And of course, that requires energy. So it's like simulated annealing. You heat something up and you go from one state to another state, but then when it cools down, it will go to a different state. And of course, all those mathematics and thermodynamics in there can be monitored, but biology, you know, when we do that to perform a molecular dynamic simulation on a specific protein, see how it moves around, you have an alpha helical bundle and how that moves around. You're looking at something very specific that is actually following Newtonian laws, which is a huge mistake, because we try to understand a quantum problem using algebra and Newton's laws, which looks good on a computer, but have nothing to do with real life.
Thank you very much, Professor Vlahakis.
Thank you.